Excellencies, ladies and gentlemen, good afternoon. My name is Latifa Youssef, and I will be your Master of Ceremonies today. It is my pleasure to welcome you all to the second day of the virtual 5th International Rain Enhancement Forum, held under the patronage of His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs. Our event is organized by the National Center of Meteorology through the UAE Research Program for Rain Enhancement Science. Yesterday's IREF sessions highlighted a number of key issues, focusing on the large-scale theme impacting water security, and zoning in then to the positive contribution of rain enhancement and the important role it can play. The transitioning from research to operations, in addition to the challenges and roadmap for this science's future, were discussed, and the role that artificial intelligence and intelligent systems can play was presented. Distinguished guests, today's agenda includes 3 sessions on different aspects contributing to enhancing rain enhancement efforts. The first is on the science of cloud formation and rainfall in the Arabian Gulf. The second is on innovations in rainfall enhancement, focusing on methodologies and new insights. The third and final session will then be on evaluation of impacts of rain enhancement efforts. Please note that you can submit your questions to the presenters, specifying your name and the presenter you are directing your question to on the online chat box. We will now begin the first session of the day on the science of cloud formation and rainfall in the Arabian Gulf. I would like to welcome Professor Ali Abshayev, third cycle awardee of the UAE Research Program for Rain Enhancement Science, to give his presentation on exploring possibilities of artificial clouds formation, preliminary theoretical results, and unique equipment for the initiation of artificial convection.
Thank you very much, Dr. Latifa. Dear ladies and gentlemen, dear colleagues and distinguished guests, our project is devoted on exploring possibilities of creating artificial updrafts and clouds in a cloudless atmosphere. At the beginning, we considered 3 different concepts of artificial updrafts creating. The first one was using special multi-level blackened surface aerostat device proposed by our colleagues from Moscow Physical Institute of Russian Academy of Sciences. Second concept is an artificial aerosol layer on area about several square kilometers by using special tiny aerosols effectively absorbing solar radiation in order to heat local volume of the near-ground atmosphere. And the third concept is the jet aerosol method, based on the use of aviation engine and special device to rotate jet stream of heated gases upward. In the third year of the project, numerical simulations of artificial convection have been continued using different types of theoretical models. Aerosol jet method was chosen as the main conceptual method for stimulating artificial thermal convection in the near-ground atmosphere, and it has been essentially improved this year. A set of special devices and instruments was designed, manufactured, and delivered to United Arab Emirates for the field campaign, except for the wind lidar and temperature profiler, which will be sent soon. The difference of our approach with the jet aerosol method is that we propose to use additional hygroscopic particles in a high concentration to be injected into the jet which should lead to the condensation process below the cloud base level in order to support the buoyancy force of the updraft. Theoretical modeling made in collaboration with our colleagues from the Northern Caucasus Federal University showed that if we supply additional condensation energy below the natural condensation level, then we can expect significant increase in the buoyancy and the updraft velocity. And our artificial updraft is to achieve the natural condensation level and go to the higher altitudes. For that purpose, we plan to use different types of hygroscopic materials, which are calcium chloride having hygroscopic point 6% of relative humidity. It means that at very small relative humidity, this such tiny hygroscopic particles may start the condensation process. Then calcium chloride hydros starting condensation from 28%, and then nitroamorphosca from 49% of relative humidity, carbamide from 72%, and pure salt from 75%. All these materials are environmentally safety and widely used in our life being. So the idea is to utilize all these at least 3 types of seeding materials at the same time by injecting them by different devices into the jet. So some of them will start the condensation process first on the lower level. Another one will continue the condensation process on the middle level, and the last one will again continue the condensation on higher level. And by this, we have high chances to reach the natural condensation level or cloud-based level. This is a simple illustration how complex are the physical chemicals chain of processes when we use hygroscopic materials and we dissolve them in water. There is not only the condensation evaporation energy, but also the thermal reactions. For example, here in our case, we used 100 milligrams of water and 50 milligrams of carbamide, and we dissolved carbamide in water. The beginning temperature was 28 degrees, and at the end it was 7 degrees. So temperature dropped it down for 20 degrees. So it is so-called endothermal reaction, when energy is extracted from the environment to modify the lattice structure. And it is logically correct to expect opposite process, exothermic process, when energy is going back to the environment in the same value of the heating. Pure natrium chloride salt, the temperature dropped down only for 1.4 degrees. So you can see the big difference between features of these materials. This is a closed system of equations of the jet stream model developed by our pioneer, Professor Kachurin. And with our colleagues from the North University, we adopted this model and found really interesting results. Here, we used a windless atmosphere, simulated windless atmosphere, surface air humidity 55%. We simulated different temperature lapse rates and retarding isothermal layers from 100 to 1000 meters. And when the temperature lapse rate is 8 degrees atmosphere, when atmosphere is very unstable, we can penetrate retarding layers of thickness 900 meters and reach very high altitudes above 12 kilometers in case we supply additional heat energy below the condensation level. I forget to mention that we plan to introduce about 2 to 3 tons of hygroscopic materials into the jet during 1 hour. When the temperature lapse rate is about 7 degrees per kilometer, we can see very interesting situation. Below the condensation level, the updraft is decelerated, while when we penetrate the retarding layer, the updraft is again accelerated. When temperature lapse rate is 6.5 degrees per kilometer, when retarding layer thickness is less than 300 meters, the updraft does not reach the condensation level. But if retarding layer is from 3 to 700 meters, the updraft have chances to pass through retarding layer and get to the condensation level, and even higher. When retarding layer is 800 meters, updraft reaches only 2, 3, 4 kilometers level. When temperature lapse rate is 6 degrees, the updraft passes through condensation level, but not too high. Thus, retarding layers of a certain thickness contribute to the development of cloud convection in the case of release of latent heat of condensation on hygroscopic aerosol. This is very well in agreement with real nature. When we observe severe thunderstorms, powerful convective clouds, they usually develop when we have retarding layer in the subcloud layer. And even when the atmosphere is unstable, but there is no retarding layer in the boundary layer, we very seldom observe severe thunderstorms. So attention is drawn to the pulsating nature of the updraft speed. Next slide, please. This is a three-dimensional view of updraft. And again, in case of a feed jet, the retarding layer promotes the development of convection due to the release of condensation heat, an increase in the temperature of the cloud jet and its buoyancy. Next slide. Oh, back please. Yeah, when we have advective wind, horizontal wind, but not very strong, we observe the inclination of the updraft. In this case, it varies by the rule shown in the middle of the slide. And we can see some inclination. From one hand, advective wind can destroy the updraft by carrying it away. But from other hand, it increases the vortex of the jet, making it more stable. Next slide. Here you can see results, back please. Here you can see results obtained by our colleagues from engineering company TESIS from Moscow. They used computational fluid dynamics model, Flow Vision, developed by their team. And they used supercomputer and accounted very tiny peculiarities of updraft in non-compressible and uncompressible and compressible regimes. And results obtained by this model are less optimistic, but still they demonstrate differences when we work in one situation or another situation. For example, here the temperature lapse rate is 6.5 degree per kilometer, and you can see the temperature field and updraft fields. On the left half of the updraft, there is situation when we don't supply additional condensation energy below cloud base. And on the right half of the updraft, there is a situation when we supply additional heating due to condensation hygroscopic particles. Then we did tens of simulations. Next slide, please. And here you can see the difference when we increase twice and 4 times increase in the energy released during the condensation process. And you can see the difference in updraft ceiling and velocity. And it could be achieved by increasing the amount of it could be achieved through the increasing the amount of hygroscopic material release it to the jet, and by using different type of hygroscopic material. Next slide, please. Here you can see how dangerous is the strong advective wind. It can easily destroy the updraft. So our purpose is to find situations when atmosphere is suitable, favorable. And this could be achieved by using state-of-the-art instruments like wind lidar, temperature profiler, and other sensors. Our goals for the field campaign are to test the effectiveness of the aerosol jet method for updraft creating, to verify the method for selecting days with favorable conditions for initiation of thermal convection, instrumental study of characteristics of updrafts depending on thermodynamic characteristics of the atmosphere, comparison of the results from numerical simulations and from in situ measurements, field measurements, development recommendation on optimization of the jet aerosol method, and technology transfer. Next slide. We found at least 3 different candidate places for the field campaign, which are on the eastern side of the country in mountain area. The idea to work on mountain is to be closer to the cloud base level. And there are Jabal Jais mountain, Jabal Mibrach, and Jabal Heben mountain, which summits are on 900 meters and up to 1.6 kilometer. There are some advantages and shortcomings like road access, electricity, public access. This is the illustration of the equipment to be used on the field site, which are the jet engine, control container, fuel container, temperature humidity profiler, weather station with pyranometer, wind lidar, a water container, water solution mixer, hygroscopic water solution container, and two types of fog cannons, and a set of nozzles directly on the output of the engine. So these two fog cannons and a set of nozzles on the output are to be used for the spraying of tiny water droplets with dissolved hygroscopic materials. These fog cannons will provide us droplets having size from almost 0 to 15 to 12 micron. So after evaporation of these tiny droplets, the remainder will be the solid, the dry hygroscopic particle, which then should promote condensation process below cloud base. And if we achieve the natural condensation level, then we have high chances to have positive result. And in situ, we plan to measure the updrafts parameters in situ by using self-designed weather drone. These are fog cannons and diesel gen set to supply the power, the working fluid mixer, flexible water tank. This is the weather drone with acoustic wind sensor, 3-dimensional, temperature, pressure, humidity sensor, and aerosol sensor on board, and illustration of our test flight on 1 kilometer altitude and data collected during this flight. The wind lidar, which will be provided by our colleagues from Finnish Meteorological Institute, the team of Hanel Karhonen, will allow us to find a situation when atmosphere will be calm, and temperature humidity profiler, which will be provided by our colleagues from Typhoon Research and Production Center from Russia, will help us to find situation when atmosphere will be unstable above the condensation level, and there will be a moderate weak or moderate retarding layer below subcloud layer. And everything will be measured in real time. This is a thermal camera and the temperature field of the updraft collected during field trial in Russia. We will measure the updraft characteristics up to several hundred meters. We prepared the list of procedures to select favorable days for experiments and favorable conditions. If atmosphere meets these conditions, then we will decide that it is a working weather. And the decision to carry out or not to carry out operations to create artificial updrafts can be made on a randomized basis. But the first 5 experiments are planned to be carried out on all working days. We have published 4 papers. The last one was in atmospheric research last year, and another paper is almost ready and will be submitted very soon. We obtained 2 Russian patents of invention, and it's a national level, and we submitted PST application to be able to submit application on international level. So aerosol jet method has been chosen as the main conceptual method for stimulating artificial thermal convection. In addition to the energy of the jet itself, in order to maintain its buoyancy, it is proposed to introduce 3 types of hygroscopic micron-sized particles into the jet, which will facilitate condensation of water vapor at lower level and provide additional powerful heat source. Our calculations showed that energy replenishment of the jet during its ascent in the atmosphere is of great importance. The fed jet rises much higher than that without feeding and overcome retarding layers, moderate retarding layers, and significantly expand range of atmospheric conditions when we can work. The influence of retarding layers on development of convection is unambiguous. In one hand, retarding layer slows down the convection but increases the swirl. But from other hand, it promotes the expansion of the jet and stimulates the development of cloud convection. The unique devices and scientific instruments have been delivered to UAE from Russia and China. Wind LiDAR, Halo Streamline, and Temperature Profiler RPG HUD Pro should be transported soon from Finland and Russia. These tools should facilitate the selection of favorable atmospheric conditions and assist in the detection of updraft in real time. Full-scale experiments in UAE are scheduled for the next few months. Thank you very much for your time and for your attention.
Thank you, Professor Abshayev. I now invite Dr. Lulin Shui, third cycle awardee of UAE REP, to give his presentation on aerosol, cloud, precipitation, and rain enhancement in the Gulf, an overview of the UAE nature research.
Thank you, Latifa, for the introduction. And good afternoon, good evening, and good morning to everybody from around the world. It's a very special you meet this way virtually. I think it became a norm after the pandemic, but I really miss you, all my great friends. I hope we can have a chance to meet together soon, probably next year, and then enjoy the meetings in person. As Latif mentioned, this is an overview of our project, especially on the modeling side. And I'm here presenting all the contents on behalf of our entire UAE Nature team. Here I have the introduction more on the on the text, but I think we'll go through the contents in the next several slides to show what we have accomplished. The Arabian Gulf region is very unique due to its surrounding areas, environments with mountains and sea surface, and also dust loading, sea salt, and industry pollution that actually made the aerosol background very complicated. And then that all in fact affect the cloud and precipitation formation, but also impact how rain enhancement will be conducted or affect the cloud. And our talk will walk you through for our different aspects of the modeling components that are covering different scales and scales of the phenomenon, including regional, meso, and local scale, also down to very detailed cloud scale itself. And here I will show some example of our approach. As everybody knows, the atmosphere phenomenon, especially cloud and precipitation, is a multi-scale phenomenon. It spans from the very small scale from millimeter as its native scale for droplets to global scale, including all kinds of large scale precipitation and convection organizations such as hurricane. And through the spectrum, we know it's very difficult to include every scale in the research, but from our project, we try our best to cover from the smallest native scale to about a regional scale that covering the Middle East and UAE region. Here, I would like to introduce the first part, or the large scale that in our project that we are dealing with is about a regional scale precipitation climatology study. The purpose of conducting such a study is to make sure the model is able to capture the large scale environment for precipitation formation and distributions. And these atmospheric conditions can be used in the future to actually identify the appropriate conditions for cloud precipitation formation, but also good conditions for seeding. In this study, or in this research, we set up a very robust regional climate model that can reasonably simulate the precipitation distributions and temporal evolutions using 9-kilometer grid spacing. But we integrate this whole domain for 17 years, spanning from 2002 to 18. And we now finished this production run and have a very early preliminary result to share with everybody. First, we show the comparison of the TRIM observed precipitation millimeter per day with our model 17 years averaged precipitation rate. This figure apparently show a very nice agreement between these two fields. We notice the very low precipitation in the empty quarter, and also high precipitation along mountains, ridges. Of course, the UAE region is kind of in a transition between these high precipitation band, but we actually have a good, very good spatial comparison between these observations and simulation. Now, if we just focus on the larger domain and the smaller subdomain as the region 2 only covering UAE, we compare these time series of the 17-year kind of also climatology. What we notice is that when we include the Zagros Mountain in the north, our model produced a little bit more precipitation compared to TRIM data. But over the UAE, we found the entire time series agree with each other very well between the model and the observation. Even the summertime as the dry season, the occasional heavy precipitation event are actually captured by our simulation relatively well. these four figures shows the percentage of the wintertime and summertime precipitation in the observation and in our model results. Apparently, you can see very similar spatial distribution or spatial patterns between these fields that give us the confidence that the precipitation mechanism are captured reasonably well in the model, but also the spatial distribution and their magnitude or proportion are very well represented. So this will give us very nice 4D data set through long period to study all kinds of condition. But as we all know, in the Middle East, the dust is a very important component to not only the weather, but also cloud precipitation formation. And during in 2018, in the late July, there was a big dust storm event occur, actually triggered by the Shamar wind, and these 3-day long dust storm event impact the clouds and rainfall significantly, as we can see from the satellite image that the UAE, entire UAE is covered by this storm. And our simulations from Dr. Diana Francis, actually show that these observation and model can reasonably represent the dust storm and the loading of the dust. But one shortage in the model being identified is that the downward shortwave radiation has been significantly underestimated by the model. So the dust being lofted actually changed the atmospheric structure and the stratification, and further impact the cloud and precipitation formation. Therefore, carefully and reasonably represent the dust impact is important in this region. This is animation shows once we put the dust as a the dust emission into the WRF model, we are able to simulate sort of like the dust lifting, and also kind of under the dust storm event, the more vertically integrated the dust has been simulated. So this would be a capability in the future for us to look into the interactions between dust and cloud. But also using WRF-Chem can also look into various effect of dust. Also, in this region, we notice a lot of sea surfaces, and the traditional way of cloud microphysics treating would be using a lookup table to parameterize the activation of CCN as function of the hygroscopicity, updraft, and temperature. For seesaw, it is a very large particle with high hygroscopicity, and in order to include its impact in the model, we have to add a separate component to such a lookup table approach, so that we can include the impact of the seesaw in our simulation, and also we can mimic hygroscope seeding using such approach. These figures shows just example that when we ran a hurricane case, that the seesaw emission as a function of the wind speed showing up on the left give you an idea that when the wind speed is strong, the emission of seesaw become stronger, and also when the seesaw being lifted and evected and transported by the atmosphere, we can have a very detailed 3D structure of the seesaw, and its subsequent impact on cloud and precipitation can be studied. And once we get down to local scale, sort of like in the over the UAE region, we have conducted some very high resolution simulation based on the field campaign that Dr. Paul Lawson's team led in 2019. For these field campaign, the first research flight were conducted on August 12th, and we set up our WRF model in a two nested domain and try to see if we can actually capture the cloud formation and precipitation feature and microphysical properties compared to observations. On the left, we show this 3 kilometer bigger domain, and nested within it is the 1 kilometer domain that was more than 1,000 by 500 grid points, covering the entire Hajar Mountain. And for this case, we have plotted all these outgoing long wave radiation as animation being shown on the right hand side. On the left hand side, we have the satellite observed cloud and also radar observed activity field on the lower left. So the model outgoing long wave radiation field can represent the cloud distribution in this animation. As we see in the GFS-driven simulations as the center column, the cloud form along the Hajar Ridge around 12 o'clock. And compared to observation, we're slightly downwind compared to the radar reflectivity observations, but the timing and the general shape and also evolutions are very similar between this. But the ERA interim data and the ERA 5 data, on the other hand, provide different large environment situation that cannot represent this cloud formation or convection initiation correctly. If we look at the wind field, the 10-meter low-level wind field, we notice this event is actually triggered by the land sea, the sea breeze, especially the land sea contrast, making a very strong sea breeze from both the north side and also the eastern side of the UAE border. And the sea breeze from the east actually impinge the Hajar Mountain and lift the cloud and trigger the convection. All those darker green shaded region indicate these gust fronts as a result of these convection precipitation that making the cold pool and pushing the air forward that trigger new convections. And this simulation not only give us a model field to compare with the observation, but we also can extract conditions from the simulation to drive a detailed hygroscopic seeding parcel simulation. So as an example that probably some of you have seen from Ishvan Goresti, our teammate's talk yesterday, these simulations being actually used to drive that parcel simulation. At the 11:15 UTC, the profiles, the vertical velocity profiles and the temperature profiles over the ridge point, point 1 on the left in the center of the domain have been extracted. And now we can use it to drive our detailed parcel simulation. And this parcel simulation is very innovative, that we're using a moving beam approach beneath 100 meters above cloud base, and then a fixing beam approach above it to track these hygroscopic wetting and growing of large of seeding particles, but also including collision coalescence in a higher level. I just want to quickly show one of the highlight results from Ishvan's work is that with the stronger updraft and the aerosol background in the black dashed line in the low level and the seeding material in the red line in the lower 3 panels, that shows only for large seeding particles like nanoparticle can actually broaden the spectrum as the top panel indicate. And most of the other smaller size aerosol particle or seeding materials cannot improve or widen the spectrum. And this is kind of the summary of that work is when we notice when the beneath cloud wet growing of the aerosol take place, and it has a better chance to broaden the droplet spectrum within the cloud. So here is a very nice result that we're trying to wrap up in a publication. After showing this real case study and the puzzle simulation, we noticed that the puzzle simulation still have its limitation. It's not a 3D structure that missing the, especially missing the processes of entrainment and detrainment. Therefore, we plan to, based on the simulation, extract the sounding or atmospheric profiles to drive the 3D idealized simulation and focusing on this individual convective congested cloud to simulate the seeding impact of such a system. And we also will apply our piggybacking approach to separate the microphysics and dynamics from this simulation. And this is my kind of a last slide of the talk. So after we present these more fundamental studies on the natural cloud and precipitation itself, we would like to include our novel techniques for seeding impact simulation across the scales. And within our team, we actually develop a first of its kind, the DNS direct numerical simulation model, coupled with the super droplet method, and also across a bigger scales, we can apply the WRF piggybacking to separate the seeding impact from dynamics feedback. And also the hygroscopic seeding scheme can be included to simulate the phenomena through all scales. And at the end, we would like to use some AI technology to help identify the appropriate condition in large scale for us to target the seedable cloud and seeding condition. So with all our teammates listed here in our project, and it's a huge list, but it's my pleasure to work with everyone and to get great scientific result and insight. So thank you. I would like to answer some questions in the later panel discussion. Thanks.
Thank you, Dr. Shui. I now invite UAE Rep First Cycle awardee, Professor Masataka Murakami, to give his presentation on in situ measurements of cloud and aerosol microphysical properties in summertime convective clouds over Eastern United Arab Emirates.
Okay, thank you very much, Latifa. Today, I will talk about the result of in situ measurement of cloud and aerosol microphysical property. Okay. A reliable numerical model is necessary to understand precipitation processes in arid and semi-arid region and to evaluate the effect of optimal hygroscopic and glaciogenic seeding against natural cloud for rain enhancement, because different microphysical property of aerosol and cloud can yield a varying seeding effect. To validate and improved model simulation performance, aircraft observation of microphysical property of diurnal convective cloud and ambient aerosol particle, in addition to seeding experiment in cooperation with NCM seeding aircraft, were conducted over the eastern mountainous area of the UAE in September 2017. Today,
I present aerosol and cloud microphysical property to better understand a mixed phase convective cloud, which are characterized by high ice particle concentration in relatively warm cloud with top temperature of approximately minus 12 degrees Celsius. Next slide, please. Next slide. Okay, thank you. This shows the instrumentation of Japanese King Air B200T and NCM's seeding aircraft C-90. We equipped King Air with various airborne instruments for aerosol cloud precipitation measurement. This instrumentation has a strong benefit, which measures both CCN and IMP, ice nucleating particle. Next slide, please. We performed 14 flights from September 5th through 24th, 2017, from our base at Align International Airport. Left panel shows the older flight track and topography, and right panels show flight track for case 1 and case 2. The red circles indicate where we did in-situ aircraft measurement. Two cases, September 16th and 20th cases, were selected to show thermodynamic and microphysical structure here because we are able to obtain the vertical profile from the cloud base height to almost the cloud top. Next slide, please. So the target of our aircraft observation were diurnal convective cloud that developed in places from stratocumulus clouds formed near the top of convectively mixed boundary layer, as shown in this photo. For case 1, data was collected by penetrating about 1,000 feet below cloud top altitude, so as to follow the rising cloud top. We made a measurement of cloud at generating to developing stage for case 1 and at developing to mature stage for case 2. Next slide, please. This shows the vertical distribution of vertical wind for case 1 and case 2. Red dot means the data from updraft core, blue from its neighbor, and black from other. Although the cloud top of cumulus turret in both cases were likely a few hundred meters above the pilot line of sight, we reached the maximum height of 6.5 kilometers, the lowest temperature of minus 9.5 degrees for case 1, and 6.1 kilometers and minus 9.8 degrees for case 2. Cloud base height and temperature for case 1 were 4.2 kilometers and 3.1 degrees if we define the cloud base as lowest height for continuous sampling of cloud droplet. In contrast, the cloud base for case 2 was located at 4.6 kilometers and minus 1.4 degrees in C. Vertical wind in the updraft core was mostly distributed within 4 meters per second, except for upper part of the cloud for case 1, where the maximum value of W reached almost 10 meters per second. Next slide, please. This shows the vertical profile of virtual potential temperature, water vapor mixing ratio, and aerosol concentration outside the cloud for case 1 and case 2. In the two right panel, a blue dot indicates concentration of aerosol particle larger than 0.01 micron black larger than 0.1 micron, and red larger than 0.3 micron. In both cases, the virtual potential temperature was nearly constant from the surface to approximately 4.5 kilometers, and monotonically increasing above that level. Although the water vapor mixing ratio was highly variable in the cloud layer, and the background aerosol number concentration were scattered in the vertical profile, they tended to be constant or gradually decrease up to cloud base height, followed by a general rapid decrease. Next slide, please. Okay, this shows the CCM spectra for 10 flight when the instrument performed very well. Data from each flight was fitted to a power law curve. The value of the coefficient C and the slope K represent the typical value for continental air mass. The CCM number concentration in case 1 were higher than those in case 2. Next slide, please. This is the vertical profile of cloud droplet characteristic. From left to right, number concentration, medium volume diameter, and liquid water content from the FSSP measurement for case 1 and case 2. The maximum number concentration of the cloud droplet were 600 to 800 per cubic centimeter in both cases, while the number concentration tended to remain constant or slightly decrease with increasing height. Medium volume diameter generally increased with height in both cases, although in the upper part of the cloud for case 1, data points were largely scattered, and liquid water content also increased with height, and liquid water content in the updraft core region was close to the adiabatic liquid water content compared to other regions. Next slide, please. Okay, to examine the ice particle distribution in the cloud, we plotted the relationship between the number concentration and the mean volume diameter calculated from CIP and PIP probes for each cloud layer for case 1. The number concentration is represented by the CIP measurement of particle larger than 100 micron to eliminate cloud droplet count. Near the cloud top, the ice particle concentration was generally lower in the updraft core region, say a few particles per liter, than in the other two regions, say several tens per liter, whereas the mean volume diameter was larger in the updraft core region. So here we showed only the result from case 1, but case 2 shows a similar result. Next slide, please. Okay, we estimated the ice nucleating particle number concentration at the cloud top temperature, say minus 12 degrees in Celsius, using two methods. One method is based on the measured INP concentration at minus 25 degrees. And INP concentration at minus 12 degrees, that is shown by open triangle, estimated accounting for both the temperature difference, I mean the minus 12 to minus 25 degrees, and then the total surface area ratio of aerosol particles measured with exterior probes and interior probe. The temperature difference of the Niemann et al. 2012 parameterization is used for correction of temperature difference. The second method is based solely on the Niemann parameterization at -12 degrees, using only total surface area of background aerosol from exterior probe measurement, and estimate INP concentration, open diamond and open square. These two estimation methods suggest that range of INP number concentration at the cloud top temperature in both cases are on the order of 0.1 to 1 particle per liter. However, please note that owing to the non-availability of sufficient quality data for case 1 and case 2, the measured and estimated INP number concentration shown here are the result for September 21st case, but which represent typical value obtained during the IOP. Next slide, please. So this is the particle images measured with CIP. This indicates most particles are round with a jagged edge, suggesting the gravel-like ice particle. Certain spherical particles were hollow in the center, suggesting that they may be a drizzle. These observations suggest cloud droplet could be frozen by immersion freezing nucleation of dust particle, and larger droplet, I mean drizzle, would form gravel embryo. Okay. So finally, in conclusion, two cases were selected, both of which are mixed phase clouds with relatively cold cloud base temperature and warm top temperature, where gravel particle was the dominant type of solid precipitation. Oh, sorry, next slide. Yes, next slide, please. Yeah, two cases were selected, both of which are mixed phase cloud with relatively cold cloud-based temperature and warm top temperature, where gravel particle were a dominant type of solid precipitation. And the aerosol particle and cloud condensation nuclei measurement indicates that air mass has a continental nature, resulting in high cloud droplet concentration of 600 to 800 per cubic centimeter. Comparing the number concentration of aerosol, cloud droplet, and the CCN spectra near the cloud base, we can infer that background aerosol larger than approximately 0.1 micron activated into cloud droplet at water supersaturation of 0.1 to 0.5%. The ice particle number concentration in the updraft core were a few particles per liter, which is similar to the primary ice nucleating particle number concentration, estimated from immersion freezing of high concentration dust particle in the convectively mixed boundary layer. Droplet with larger size, I mean drizzle, form a gravel embryo, and the ice particle number concentration were several tens of particles per liter outside the updraft core in the upper level, which were produced by secondary ice production mechanism and or the accumulation of ice particle produced by primary ice nucleation. Next slide, please. This is the last slide. Yeah. Okay. Our ongoing work is numerical simulation of observed convective clouds using CREST 4 ice model to validate against observation and improve microphysical scheme, and to investigate the impact of secondary ice production mechanism and accumulation of ice particle generated by primary ice nucleation mechanism. And near future work is numerical seeding experiment of diurnal convective clouds using CRESS 4-eyes CCN model to optimize seeding method, or say seeding condition, and evaluate the maximum seeding effect. Thank you very much for your attention.
Thank you, Professor Murakami. I now welcome Dr. Dion Terblanche, expert consultant on weather and climate at the World Bank, to moderate the audience Q&A panel discussion with this session's 3 presenters.
Dear colleagues, we have a fairly short panel discussion this afternoon because we have had quite intense 3 presentations now. And so without going into lengths of introducing the panel, you can see the background and the affiliation on the program. I want to kick off with Professor Ali Abshayev in terms of the creation of artificial clouds. This has always been a dream, to create clouds from nothing, and we see that nature actually does this. When we have big fires, biomass burning, volcanoes, and then something that's not nature, but the ultimate extreme example is when there's an atomic explosion that we see also clouds rapidly forming due to the heat source. So I just want to know about the horizontal wind issue. We have spoken previously about the horizontal wind and how that is probably the biggest challenge that you will sit with when creating an artificial updraft and hoping that you will reach the condensation level. And by the way, the audience is also welcome to send in questions. So we will have about 10 to 15 minutes. So it's a short one. So Ali, short answer, please.
Thank you very much, Dion. Indeed, horizontal wind is the main challenge for our approach. And in this term, we plan to utilize dedicated instruments because there are favorable situations, and we need to identify those situations and start our trial, our intervention when we have such a situation. And according to numerical simulations, we found that the most dangerous is the subcloud wind near the surface. The wind above the condensation level is less challenging. So in case the wind speed is from 0 to 5 meters per second, we have a chance. In case we have stronger wind, there is no chance.
Good, thank you. Lulan, yesterday I mentioned that the whole issue of rainfall enhancement is actually a very sophisticated forecasting problem. Because if we could simulate the atmosphere and forecast future conditions perfectly, it would have been quite easy to predict what the outcome of a seeding intervention would be. Now, you have done quite impressive ensemble of modeling exercises from the very detailed DNS up to climate scale. I would like to hear your opinion on when you believe our modeling efforts will become the main evaluation tool for cloud seeding and rainfall enhancement experiments.
Thank you, Dion.
What are the stumbling blocks?
Okay, yeah, thanks for the question. I think most of us on the stage actually have that thought and belief that at a certain point, a numerical model probably is good enough for us to understand the nature and also simulate or quantify the seeding impact. And in my opinion, because the whole cloud and precipitation, including rain enhancement processes, are multi-scales, we are not able to isolate these this phenomenal scale by scale because they're linked. Through these energy propagation and through the chaotic interactions, any changes at a certain scale will actually propagate. So it's kind of difficult to have one model to actually simulate all the scales in the perfect kind of a sense to link everything together. So in my opinion, do is based on these different scales that we know from the simulation, and we can expect certain observable quantity or observable features that can be validated by the observations so that we have confidence that the right processes being captured. And we combine all this knowledge together to kind of lead to a more confident kind of results on the quantitative effect on precipitation enhancement. In my opinion, unless the quantum computer is available for everybody, it's really hard to say that we can simulate from the droplet level to the regional climate level in one model and get the quantitative correct. But when we actually do the scale by scale investigation, we're able to find trace that can be validated by observation. Once that steps are established, we can only say we have more confidence, but we cannot say we're for sure this is the exact amount that we get from the ring enhancement. So that's kind of my perspective, and hopefully that answers your question.
Yes, Lulan, that's very interesting. And of course, all the work that's been done and also the work that you've been doing in your project eventually contributes to a much wider field, including the field of weather prediction at all timescales. So it all starts with the cloud microphysics, and many of the biases that we see in models can be traced back to not being perfectly captured in the model. So we also hope that artificial intelligence methods will help us in future, but of course that is also a data hungry process. And this brings us back to the issue of how important it is to capture data, to catalog it properly, to analyze it properly, so that these learning systems can feed on the data that's been selected. So I would like to turn to Professor Murakami. He brought his aircraft from Japan to do studies in the UAE. And he flew also during those flights his instruments and collected a lot of data. I think it would be interesting to hear from you how the atmospheric conditions in terms of aerosols, cloud properties, and so on differ over the UAE, because it's really complicated there with all the influences from dust, sea salt, the industrial oil refineries, the topography, etc., compared to what you saw as you flew over the maritime regions back to Japan. Can you just paint us a picture of shortly how clouds and the atmosphere change along that route?
Yeah, actually, the cloud over the UAE very much influenced by the dust particle, very high concentration of dust particles, say several particles per cubic centimeter. And this acts as a very good ice nucleating particle. That's why we have a rather high concentration of ice particle, mainly grapple-like particle in a rather warm cloud. So probably the numerical model first realistically simulate this situation, and then we need to do a numerical seeding experiment to study the optimal seeding condition and also evaluate the seeding effect. I think so. So that particle is a key for the cloud formation over the UAE. I think so.
Okay, and when you flew back to Japan, where did you find the cleanest environment in the atmosphere, where one would expect the most efficient processes in terms of rainfall formation? Where along that route?
Yeah, actually, on a ferry flight, we also did some measurement, especially the aerosol measurement, and then we detect the dust storm from Middle East, say up to the Philippines. So I think the dust storm from the Middle East has a very big influence on over the Indian Ocean and also the part of the Pacific Ocean. I think so. Yeah.
Yeah, definitely. That's very interesting. So just to wrap up, I would like to hear from each of you in 2 sentences. What did this UAE REP program provide you as scientists in terms of your advancement in the study of rainfall enhancement and understanding of atmospheric processes? So Ali, I would like to start with you.
Okay, regarding our project, it's a fundamental research. So we believe we will get new data, new knowledge about the updraft formation, particularly in the mountain area of the UAE. And it will help us to maybe imagine if we will have a chance one day to create artificial cloud or not.
Dion, you are muted.
And your colleagues.
So,
Okay, maybe I should be the next one, even though we cannot hear Dion. I think UAE REP opened up a great opportunity for the entire international research community to come back to a very controversial topic on the cloud seeding. But at the same time, this opportunity actually link all the researchers together to look at the very fundamental cloud physics, dynamics, and even regional climate issues that actually broaden the research topic and actually improve the knowledge and help link all the researchers together. So I would say this is a great program that helped the entire research field and atmospheric research field to look at these very important questions.
Well, I hope you can hear me now. I'm not muted. Can you hear me?
For me, the UAE program gave me an opportunity to study the hygroscopic seeding for the warm cloud and mixed phase cloud. Before that, I have rather plenty of experience in glaciogenic seeding, especially for orographic snow cloud. But hygroscopic seeding still has many, what shall I say, questions. And then what I did in this program is that usually many people believe that the hygroscopic seeding is very efficient to increase precipitation from warm cloud through enhancement of collision coalescence processes. That means increase the cloud droplet. But for the mixed phase cloud, probably such a hygroscopic seeding trying to increase the cloud droplet may not work very well. On the other hand, the increase the number of cloud droplet, decrease the droplet size may work to enhance the precipitation from mixed phase convective cloud. This is it was a very good opportunity for me to do such a hygroscopic seeding study in this UAE research program. Thank you very much.
Cool.
Okay, so there's something that happened. So apparently we've got a question from the audience. So if we could see that. somehow, then we can maybe deal with that. No, it doesn't seem like I can see a question at this stage.
We can see
So
it
let's,
at the bottom.
Can you see it there?
Yes, I think I can speak out if you want me to. So Dave Deline, University of North Dakota, for all speakers.
I can't see it. Lulen, if you can read it, then it's good.
Yeah, I'm reading it. Can you hear me?
Yes.
Okay.
Yes.
Yeah, from Dave Deline, he asked for all the speakers. All speakers talk about and use models. The models are based on observations. Some very detailed, such as Professor Masataka Murakami's measurements. Once this model are developed, can you discuss evaluation of the models in a real atmosphere? How do you feel is best to evaluate, or what is possible? So this is the question.
Okay, so it's to all three of you, but we need to keep it very short because we're running out of time, and we are, so keep it within a few seconds. So I would like to hear from each of you. Ali, start.
Okay, indeed, in our project, we utilized several different types, different scale models, but we found that no one model performs what we really need. So we did a lot of adaptation work, and we are on the long way to adapt other very widely used models like Wurth model and other types of models, cloud resolving model. So unfortunately, there is no one model available for public access that we can utilize for our purpose. So we still have to do much in this model development work, and to collaborate with other teams like we did in our project with engineering companies that did a lot of simulation for different engineering tasks. So, and with other groups also with cloud resolving models. And we must do a lot of work to improve the performance of this model. And the first step, which we plan to get maybe this year, is to validate those results we obtained so far with real measurements. So
okay, so Ali, let's move on to Lulen. Lulen, your views on this question?
Thanks, Dave, for the question. As you mentioned, to evaluate the model in a real atmosphere, and first we have to have a really good and accurate observations of the atmosphere. But most of the time, that what we can observe is a state or a result of a history of a processes. We are not observing processes. We are observing the outcome of processes. So, in my opinion, we definitely need to collect these in situ observation and remote sensing observations to at least validate these this kind of state and results. But we also want to have more processes level kind of the measurement to help us actually quantify these physical processes. In my opinion, we need to still combine both laboratory observation and real atmosphere observation to validate our model result.
Thank you. And Masataka, your view shortly on this?
Okay. So to validate a three-dimensional model, we definitely need a kind of field campaign. Aircraft observation was something we know. That's why we did aircraft measurement over the UAE in 2017, and also the more detailed microphysical processes represented by in a partial model. We probably need a laboratory experiment. For example, the crowd simulation chamber experiment. These things are very much important to improve our knowledge and our technical scheme in a numerical model. I think so.
So thank you. With that, I would like to thank the panel and also the presentations that they did beforehand. And let's move on. Thank you very much.
Thank you.
Thank you very much to our moderator and panelists for these informative contributions to the understanding of cloud and rainfall formation. We will now begin the second session of the day on innovations in rainfall enhancement. I would like to invite Professor Martin Ambum, member of the IREF Second Cycle Awardee, Professor Giles Harrison's team, to give his presentation on electrical aspects of rainfall generation, latest results.
Good afternoon, everybody. It's a pleasure for me to give this presentation on behalf of the whole team, in particular my co-Is Kerry Nicol and Giles Harrison. To start with, I'd like to remind you of the fact that our whole project basically contains quite a lot of ingredients. Just remind you of the ingredients. So we have several strands. One is a modeling, in particular direct numerical simulation modeling of cloud microphysics, where we are particularly focusing on the electrical interaction between individual drops. This needs to be our model, and I will explain that in a second. And the other strands are more experimental. So in the second strand, we worked on the characterization of electrical environment in the UAE with automated weather stations, which were augmented with electrical measurements, the first done in the UAE region. And the third package, which we call charge delivery, it's essentially using UAVs to deliver and to measure charge in the environment. And I will show you some of the latest results on that. So to go to the modeling side of things, so here's an example, just a demonstration example of the kind of work we do. We try and follow individual droplets and try and simulate what they do by individually interacting. We need to do it this way because the normal stochastic cloud microphysics models that we have heard a lot about are not able to accurately capture the kind of effects we're trying to simulate. So what we're trying to understand is, if drops are charged, how does that change the interaction? How does that change the collision and coalescence process and ultimately the rainfall formation? You can't do that in stochastic models or standard cloud microphysics models simply because we do not know how the electrical interactions between individual drops do change the collision kernels. So that is what we've been focusing on, trying to use these DNS simulations to find that out. And I'll just give you really only very brief examples. There's many examples, of course, that I could give, but no time to do it. For example, on the left-hand plot, you can see as a function of two drops of with their ratio of radii on the bottom, how much the presence of electric charge increases their collision rate. And you can see that, well, there's several complicated effects happening, but there's typically an enhancement of several percent in terms of collision rate. And that is actually quite an unusual and surprising outcome, especially given that these are drops that have a uniform charge. So they all are, for example, positively charged. And there is a Coulomb effect, which repels the drops. And there is an image charge effect, which is extremely complex to calculate in detail, but we had to do that, which attracts the drops. And so these effects are essentially compensating, get compensating effects on the collision rate, on the coalescence rate. And it's very hard to disentangle those two things. But what we found is that in different circumstances, the two competing effects, the Coulomb repulsion and the image charge attraction, in one regime, one of the effect wins, and in the other regime, the other effect wins. And so I won't have time to really explain the right-hand plot, but what you see is the formation rate of a particular, the rain formation rate of a particular cloud drop population. And what we've done in the various simulations there is enhance the collision rate for like size drops and reduce it for different size drops, and the other way around. And by doing that, you can get compensating effects, and you get rain formation at very similar times, even though you've changed the collision rates tremendously at different population sizes. So what we find is for drops of similar size, electrostatic charges tend to be dominated by the Coulomb interaction, and they tend to repel. And the reason for that is that drops of similar size are spending a lot of time together. Whereas drops of different size, they tend to collide more, and that's where the attractive interaction between the image charges is going to win. A second aspect of our direct numerical simulations was how the electrical charge on aerosols and drops would influence the capture of aerosols, and we're particularly looking at hygroscopic aerosols here, the capture of aerosols by drops. And we find, interestingly, that charging of aerosols or drops does not actually make an order one difference on the capture rate of aerosols. And so we find in a turbulent flow, the capture of aerosols by drops is dominated by turbulent flow scales, and we have been able to exactly determine the size of this flow scale as a function of the turbulent parameters. And at the same time, you can pretty much quasi-analytically predict the uptake of aerosols by a particular droplet population. And as I said, the charge does not make a difference to the uptake of aerosols, which is another very surprising result. But what that does mean is that if the aerosols were highly charged for some reason, and I will show you some results later demonstrating this, if the aerosols were highly charged, then the drops will readily take up these aerosols and take up the charge. So what we've demonstrated here is that charged aerosols are going to be a very effective way of charging up drops. This is just a kind of an addition which we hope might indicate something to look out for in the future. Is of course, our models also predict somewhat familiar things, like if you introduce medium-sized or very large aerosols, I would say, around the 30 micron radius, that you get extreme enhancement in rainfall formation in the time for it to produce rain. So the blue curve, for example, is a control run where you can see rain in this particular population being formed after about 90 minutes. It's just an example here, but by introducing a tiny amount of 30 micron large aerosols, which, for example, in the yellow line, produces in the same drop population rain after about 20 minutes. So that's a speed up by a factor 3 or 4. The problem, of course, with the introduction of aerosol, and this is something that even in nano adjusted aerosols is a problem, is that as soon as the aerosol gets hydrated, it just becomes like a dissolved drop. So there's a problem with making these large drops keep their hygroscopicity. And so one of the things we are suggesting is that charge would be the ideal way of keeping large aerosols, hydrated aerosols, hygroscopic, because the charge doesn't change, the charge effect doesn't change on hydration of the aerosol. So that is something we would be keen to pursue next, using charge to make aerosols permanently hygroscopic. Now, perhaps the next step is to talk a bit more about some of the measurements we've been able to do. For example, we've been setting up in Airline Airport several automated weather station where we characterize the electric field, for example, by what is called field mills, which you can see on the top of the the met mass there, but we've also produced some bespoke balloon-borne instruments, and I will show you just a couple of results on this. So, for example, for the measurement of the electric fields in our line, what we found was that that many of the sea breezes that loft dust up that you can measure. So, for example, if you look on the top graph there, in the red line, you can see with the right axis the visibility. So you can see in local time there a sea breeze front coming through, which lofts an awful lot of dust, and the visibility going down dramatically. But at the same time, in the black curve on the left-hand side, you can see that the electric field, which is always negative, that means the electric field points downward. Normally it's about 100 volts per meter, but then it goes up to suddenly to 1,000 volts per meter. And the only way that that can be explained is by the aerosols, the dust that is being lofted in the sea breeze front is being highly charged. You can see, well, the plots haven't been here. So, but we find that dust, for all the cases that we've seen of sea breeze fronts, that the dust is very highly charged. So it's a standard property of dust there, and we assume that that is due to the sea breeze inducing saltation of the dust. The dust starts to scatter over the surface, and then by triboelectric effects, the dust get charged tremendously. And as we've shown in the modeling work earlier, that dust is very readily, if it's in the right location, will be very readily be absorbed by drops, by any present drops, and thus charging the drops. Other things we've done with cloud-based sensors, ceilometers. We've been studying rainfall events, so about 100 over the period that we've been observing in our line. About a third did not actually reach the ground of these rainfall events. And in fact, most of these rainfall events barely were registered by rain gauges. But what we found is the way much of these rain events are formed higher up in the atmosphere. And what we found was the importance of pre-moistening of the atmosphere for rain to actually reach the surface. So there's actually quite a lot of rain formation in the clouds, but the rain simply does not reach the surface. And thirdly, on the measurement of the local electrical environment, we produced bespoke radiosonde equipment. On the right-hand side, you can see a little schematic of that with charge sensors, optical sensors, and we are able to provide profiles of very non-traditional measurements. Say, for example, the space charge on the fourth graph there, both positive and negative charges there, and drop concentration with or aerosol concentration with our optical sensor there. So that's only just a few very short examples of the kind of measurements we've been able to put together and to characterize the electrical environment in the UAE. The final strand of these measurement things was a development, which was an independent development, kind of parallel to our project, of what we call the flare logger. The flare logger is a measurement device which is built inside the housing of the shape of a standard cloud seeding flare. So what that means is that without any interaction with the aircraft systems, we're able to put one of these devices in a standard holding for a seeding flare and make any measurements of the meteorology that we like. So standard meteorological measurements, but of course also electrical measurements and that kind of thing. So this is without any adjustment of the aircraft system. So it should be, so it's very easily deployable. One of these systems is waiting in Al-Ain Airport to be put on a seeding plane. Having said that, I think some regulations have changed, and so there is some delay in actually getting that up in the air. But it's there and ready to be flown. And then oh, right, there's a 3D CAD drawing that you can see of how it was made. This is 3D printed housing which can hold this bespoke equipment. And the third part of our project was and then what we call the charge delivery, which is basically flying UAVs with corona emitters and charge sensors and other standard meteorological sensors through clouds, and see whether we can deliver the charge and whether we can measure the charge. Now, one of the advantages, of course, of charge delivery as a way of seeding clouds is that it's very easy to do on a UAV. There's no issue with a mass or basically payload mass, because you don't actually seed out aerosols which have a mass. You seed with ions from your corona emitter, which do not essentially change the mass of your plane. And so all you need is a battery to produce as much corona emitted charge as you like. And the other advantage is you can do it you can emit charge of either sign at any rate and that kind of thing. So it's highly adjustable and highly steerable. So this platform has been flown in Finland and in the UK as a matter of test flight, and it's currently, the platform is physically in the UAE as well, and is waiting for a test flight near Abu Dhabi to be done over the next 3 months. So, for example, on the right-hand side, you can see a trace of the electric field measured at the surface whilst the charging, the corona emitting UAV is flying over the field mill, which measures the electric field. And what you can see is that as soon as the aircraft flies over the field mill, you can see these spikes in the measured electric field, which is evidence that the aircraft is essentially delivering all that charge into the air, and instead of it staying on the plane. I don't have time to talk too much about the interpretation of those measurements. I just finish off by showing this video of some of the test flights we've been doing near Bristol in the UK. You can see that the UAV is being launched via catapult. The flight track is pre-programmed and of course monitored by humans. And the flight track is programmed to go over the local measurement station, which you can see in the distance there. Currently, that measurement station there only has an electrical field mill on it to sort of see, you can see the electrical field mill at the top there, to measure how the electric field changes by the corona emitting UAV going over. And I think you saw the UAV there flying over the field mill, as seen from a drone flying over the mast. So these flights have been very successful, and we are very keen to reproduce them and see how the results change in a completely different aerosol environment as seen in the UAV. And that concludes my overview of our work in our project. Thank you very much.
Thank you, Professor Ambam. Next, I welcome Professor Linda Zhu, first cycle UAE Rep awardee, to give her presentation on porous nanoparticles, their potential for cold cloud seeding.
So now I will talk about the porous nanocomposites and their potential for cold cloud seeding activities. So first, I would like to introduce of the cold cloud seeding. We know among the various type of clouds, some clouds has their temperature profiles sub-zero degrees. So we call this type of cloud as cold cloud. And the example of such a cold cloud is a mixed phase cloud. So this type of cloud consists of supercooled water droplets and also mixed with ice crystals. So this type of cloud is very unstable. At any time, the ice crystal can grow rapidly at the expense of the cloud droplets. So this process is well known as a WBF process. The mixed phase clouds are observed in all seasons and the different conditions in different parts of the world. Another type of cold cloud is called a cirrus cloud. This type of cloud are formed at very high altitude and they made up of ice crystals. They have a look which is like a very thin hair strand type of curled up type of look. This photo was taken by myself in my balcony, Abu Dhabi. So here we also experience this type of cloud. So in terms of the precipitations, apart from the normal rain precipitation, we also have icy precipitation such as sleets, frozen rain, snowflakes, and hailstone. So where can the cold cloud seeding take place? The critical factor is this heterogeneous ice nucleation, because the pure ice will only be formed, can be formed at a very low temperature, lower than -38 degrees. But in the presence of ice nucleating particles, so the supercooled water can form ice at a much higher temperature. This makes the cold cloud seeding much easier. If we look at the atmospheric profile, vertical profile, you can see at above 3,000 meter altitude, the temperature becomes 0 and then sub-zero. So in that region, there is a lot of opportunity for cold cloud seeding. Also, I would like to mention the precipitation type is affected by the surface temperature. Even we made the snow through the cold cloud seeding, they formed ice crystals. But if the surface temperature is above 0, that means that they will melt into rain and precipitate on the surface as rain. Okay, so when will hail occur and if can cloud seeding suppress it? You know, the hailstorm is associated with a cumulonimbus cloud. This type of cloud is very dense, towering, vertical type of cloud. It has a very high content of supercooled liquid water and very strong both updrafts and downdrafts. So they look quite dark, probably indicate the ice crystal already formed. And the large size hailstones can occur during the warmest season of the year. So during that year, the sun radiation is the strongest and evaporate a large quantity of water vapor. That's why. And in UAE, we reported like in newspaper, I see this hail falls on eastern UAE. We can see the hailstone size is as large as 3 centimeters. So this region is also affected by the hailstone damage. So if we can use cloud seeding to suppress the hail, then we can prevent the hail damage and also transform these dangerous convective clouds to avoiding formation of very large hailstones. The glaciogenic seeding materials, mostly silver iodide, can be released into the cloud by either rockets or burning the seeds with the acetone or released by flares using the aircraft. The most popular hail suppression concepts include like a beneficial competition. This means we release a very large number of very small isonucleating particles and allow them to compete each other of the available supercooled water droplets and to limit the growth size of the ice crystals. Another two concept is early rainout trajectory lowering. Both are related to targeting the lower level of the cloud and accelerate the precipitation of the thing. Okay, so now I move to the cold cloud seeding activities around the world. The first I would like to mention is orographic cold cloud seeding has been reported, published in Proceedings of National Academy of Science in 2020. This is a project that was conducted in 2017 at the mountainous area in the southwestern Idaho in USA. The radars and the aircraft mounted probes to monitor the full chain of events of the ice nucleation initiating through the snow formation. If you look at the graph at the top right corner, you can see that the radar reactivity of 4 time periods. The first one is at the beginning of the seeding, and the second one was taken 30 minutes after that. They already show the initial appearance of the cloud seeding signature. And the later part of this graph shows another 15 minutes later and 15 minutes later. The lower set of the graph shows the seeding line was detected at the altitude between 3,000 to 4,000 meters. So this research provides evidence of cold cloud seeding can help to accelerate the formation and precipitation in some areas. In Europe, it also reported some hail suppression activities. So because hail is a disaster, particularly for farmers, it damages crops, fruit trees, and vineyards. A large experiment was organized in Switzerland with French and Italian team, and they delivered using rocket to deliver the silver iodine. They've done the 205 seeding cases, only report very small risk reduction, about 5%. More attempts has been tried in 1990s, including Dr. Ali Abashev's team in Russia. They reported if the suitable climates, the hail damage reduction might be in 15 to 20%. And China has reported large-scale cold cloud seeding and hail suppression activities. Their northwestern Xinjiang province has a specific climate which is dry, hot, and with rugged landscape. So they adopted weather modification to protect their farmlands. How? By firing the silver iodine packed cannon shells to disrupt the unfavorable weather fronts. They claim to reduce 70% of the hail damage every year in the region. It also increased 900 million to 1.2 million cubic meters of precipitations in the region. More recent, in 2019, the Chinese government has announced a plan to expand weather modification program, which cover an area quite large for artificial rain and snow. The photo on the bottom shows the scientist has induced the season's first snow in capital Beijing, which as early as 2nd of November, which is historically very early. Beijing is a very dry city, so this type of early snow is very welcome. Okay, now I move to the talk about potential of porous nanocomposites for cold cloud seeding. In 2019, recently, my group has developed a type of novel cloud seeding material, which is porous, reduced graphene oxide and silicon oxide nanoparticles. So each component of this material has play a role in accelerating the ice nucleation. So the 3D RGO part is serve as a template for the ice crystal growth due to similar hexagonal atomic lattice matching mechanism. And silicon oxide is a hydrophilic nanoparticle. They contribute to make the surface more hydrophilic, easy to absorb supercooled water droplets, and enable less aggregation of the overall structure, make them more porous. And later, the porosity play a very important role because that enabling the supercooled water condense in the pores, and this enhance the ice nucleation activity as showed in the illustration. Okay, the SEM image, first one is 3D graphene oxide without the nanoparticles. You can see it's very fluffy, porous. And then by adding the silicon oxide, we have a uniform distribution. Okay, we place this samples under the electron microscope with the controlled temperature and relative humidity. So we observe if we can generate ice under these conditions. So here you clearly see the ice are formed on top of these nanocomposite materials. So they're in different shape and forms. So the condition of this experiment is under -8 degrees. So it's definitely much easier to get ice. No need -38. Instead, -8 will be enough. So due to the effects of the accelerated ice nucleation reaction. We found two different appearances. One is the hexagonal ice crystal, another one is bulk ice. Okay, one or two more. So in the rough region, they have larger pores. Those larger pores trap more water vapors and more condensations. They promote single crystal growth, provide enough water vapor. And the outlook. So additional cloud chamber experiments and the airborne seeding studies are the key step to validate the feasibility of using novel cold cloud seeding materials in actual operations, and incorporate the empirical results with modeling and numerical study would be useful. Use these novel ice nucleation materials in other applications, such as hailstorm suppression, smoke fog reduction will be useful as well. That's it. Thank you.
Thank you, Professor Zhu. Next, I invite Dr. Diana Francis to give her presentation on working towards a unified multi-component atmospheric model for rain enhancement applications in the UAE.
Hello, everyone, and thank you for the opportunity to represent the latest progress on developing a unified multi-component atmospheric model for the rain enhancement applications in the UAE. This work has been performed by all the team members of the NGOs lab at Khalifa University. So numerical models became a very powerful tool that scientists are using now to better understand and improve our understanding of the processes that happens in the atmosphere. They help us also to overcome the lack of observations and to extend the spatio-temporal coverage of those. They can help us also to predict weather patterns and their impacts. But most importantly, they are a very useful tool to untangle the complex interrelation between the different processes in the Earth's system. If we take, for example, the cloud formation phenomenon, in this process, many other processes are involved and interactions between many components are in play. For example, we have interactions between land, ocean, between also the radiation and also the atmospheric composition. So if we want to understand the role of each of these processes, we definitely need models which will allow us to actually to understand the role of each of them and how it impacts the others. So that's why a lot of work is needed to develop comprehensive numerical models that include all these components, but also to assess their capabilities in representing the real world. If we take here the example of cloud formation. This is particularly true for a country like the UAE, where actually it has specific conditions, such as it's an arid region, but at the same time, it's influenced by the surrounding seas. So we can't consider it like only a desert. It has also a very specific land properties and heterogeneities from one area to another. And also the atmospheric composition over the UAE is very specific in terms of mixture between natural aerosols and also pollutants. This due to the fact also that UAE is located at a carrefour, so it's impacted by the surrounding environment and transport from other countries. So if we take a model that is developed originally for other parts of the world, it doesn't work immediately for the UAE. So therefore, there is need for adjustment and adaptation of each of those schemes to the UAE environment. So this has been the work over the last few years of the Angeos Lab at Khalifa University members to actually validate and assess each of the components that are necessary to simulate the UAE environment. But today, I'm going only to present two recent validation or assessment regarding the role of dust aerosols and in the climate over the region and how it is well simulated by the unified model. And also the second case will be on the development of summertime convection and how our model is performing with this regard. So let's start with the dust, and you won't be surprised if I tell you that the Arabian Peninsula is one of the major dust sources at the global scale. So for people living here, we witness frequent dust storms that vary in intensity, like the one I'm showing here, for example, in September 2015, where a cyclone formed over the area and caused a massive dust storm to form. And you can see how the sky looks like from the ground in Abu Dhabi. In general, Southwest Asia region contributes up to 40% of global emissions per year. So this is to say that dust aerosols are present almost every day in our area, and they have many impacts. But we still have a lot of unknowns and uncertainties related to dust aerosol in each of their phase in the dust life cycle, starting from emissions, which happens over land, to transport, which happens in the atmosphere, and ending by the deposition, which occurs over land or over ocean. So most of the uncertainties actually are located when the dust aerosols are in the atmosphere because they interact with radiation, and how they do this, they scatter or they absorb the radiation. So therefore, they will change the amount of radiation reaching the surface, but also the amount of radiation scattered back to the space. They have also, by changing the energy balance, they change the circulation. This we call it the semi-direct effect of dust aerosols. The other impact when they are in the atmosphere is the interaction with clouds. So dust aerosols can, for example, change the lifetime of the clouds, change the amount of rain these clouds can produce, but if the cloud will form or not, because freshly emitted aerosols can act as nuclei to help cloud formation. The other impact is when they are mixed to pollutants, so they can change the properties of pollutants and modify the atmospheric chemistry. My talk today will be focused on these challenges and the interaction of aerosol with radiation and clouds. So for that, I'm going to show a recent study published by our team on a dust storm occurred in July 2018 during summertime here. So here you are seeing on the left side, the satellite observation of this storm, which lasted for a few days. And on the right side, how the model simulated this dust storm in terms of dust load. So we can see here that the model captured well the amount and the location, and especially the time of occurrence of this dust storm. And if now we move to look how what was the radiative impact of the dust, again, I'm showing satellite observations of radiation fluxes at the surface on the left. So you see here the red patch is actually the increase of long wave radiation at the surface due to the presence of dust in the atmosphere. This was a surprising result and a very new result because before this study, it was thought that dust induces a cooling at the surface. But this, from the observations, we are seeing that the heating that is due to the long wave, when the dust re-emits radiation back to the surface, it causes a very large warming. So what happened now when this warming occurred? Actually, if you look at the surrounding areas, they did not change in terms of energy balance. So what caused this? We have now a different land-sea temperature gradient. So now this warming is actually favoring the intrusion of maritime air over the desert. And here we can see it in the map of water vapor. So the red patch on the bottom panel here to the left, we can see how the maritime air that is rich in moisture is able to actually cover all the UAE right at the place where this dust is located. So this impacted the cloud formation that are also observed here in the satellite imagery on top of the dust that you can see in pink colors. So some clouds developed here during this event, and also rain occurred at the ground. So this is the impact of dust. Now, if we want to investigate more how the radiation changed during this event, we can, for example, look at some ground-based observations for temperature and for long wave radiation. Let's take this example. So we have here observation at Al Ain, which is a ground station in the UAE. We can see the temperature, how it increased during the event, and it did not actually decrease to the nocturnal values as before the dust storm. So the warming was continuous during day and night during the dust event. This is due to the long wave radiation that you can see on the bottom panel, how it was increased during this storm. And this we can also see it in another station at Gassura, it's also in the UAE. And here also I'm comparing with the model. So the model is in red and the observations are in black. So we can see that the model was not able to capture the increase in temperature due to the dust storm, and was not able also to capture the increase in long wave radiation due to the presence of dust aerosol in the atmosphere. So this has implications because if the model is not able to capture this, that means it will not able to bring the moisture that the dust brought by impacting the radiation. So another sensitivity study to the dust and what are the impact on rain and cloud development in this ongoing work, where we one way to check on this is to do simulations with the impact of dust on cloud, and another one without the dust impacting the cloud. And then when we compare both simulations, we can see what could be the impact. For sure, this still needs to be validated, but it can at least give us insights on the impact. So here I'm showing to the left the simulation with dust impacting the cloud, and on the right, the simulation with no impact of dust on the clouds. Our results show that for simulation with dust, there is an increase in the amount of rain that we can obtain compared to simulation without interaction with dust. And if we want to understand why this result was given by the model, so here to the right, you have two panels, one on the integrated water vapor. It's comparing simulation with dust minus simulation without dust. So we can see the positive areas are areas where, so the color green, the green colors are area where the atmosphere is more moisture than, there is more moisture in the atmosphere than the other areas. So what's happening actually is the presence of dust is making the atmosphere more moisture, as we saw also in the previous case. And if we want to know why this, we can investigate the wind speed, how it changed between the two simulations. So this is the bottom panel, and we can see increase of wind speed in the simulation with dust compared to simulation without dust aerosol. And okay, now if I move to the second project, which is about the summertime convection over the UAE. These convections are very rare, but still they are very important. So the idea here is to understand what are the processes that favor such development of convection, and how is the capabilities of the model with this regard. So what we found is that if we want to have convection developing over the UAE, there are many ingredients to be reunited. So first, if you look at them on the vertical, so if we start at the surface, if we have orography that can trigger the convection. Now, if we look at the conditions at low level, meaning from the surface up to 2 kilometers in altitude, we need to have a strong temperature gradient between land and surface, also strong moisture gradient between land and the sea, and most importantly, we need to have wind conversions, which luckily is brought to us by the movement to the north of the intertropical front. We know that this intertropical front moves during summer months over the UAE, which actually brings this convergence over the UAE and favors the development of summertime convection. Now, at the upper levels, if we have a trough, meaning a disturbance from mid-latitude and from the upper atmosphere, this also can trigger convection. But the necessary conditions are really at the low level. Surface and upper level can be a trigger. So how does this look like in real data? So here I'm showing maps of 2-meter temperature. So these are the bottom panels. 2-meter temperature and 2-meter water vapor mixing ratio. And you can see the strong and the steep gradient between sea and land on both panels across the UAE. So the green line here indicate the gradient. And we quantify it to be, so in order for the convection to develop, we need this gradient to be higher than 10 degrees Celsius. And for the water mixing ratio, it has to be higher than 10 grams per kilogram. The intertropical front during summer is here represented by the blue line, so the ITD. And we can see actually the convergence between the southerlies and the northerlies, and this line, this front that is between them, crossing the UAE, and then at the end of August, it will cross again to the south. On the upper level conditions, you can see the presence of trough, for example, now here over Iran and Pakistan. that can trigger the convection in our case. Now, if you reunite all these conditions, you get this beautiful convection development seen here in the satellite observation, mostly where the orography is present, but also development later during the day over the desert in the UAE. Now, how about the model performance? So now if we check if the model is getting it right, like the observation, unfortunately, the model could not simulate the development of convection, even if we go to very high resolution of 2.5 kilometer, and despite modifying the forcing parameters and the different data set for initialization of the simulation. So we have run some sensitivity studies to figure out what had caused this discrepancy in the model. And the first indicators point to the soil moisture and how the soil moisture is represented in the model. So basically, we need more observation about the soil moisture in the UAE to be able to replicate it in the schemes used in the unified model. Now, so this takes me to the last slide for my conclusion and some perspectives. So our results highlight the limitation of regional models in arid and hyper-arid regions, and the need for the development of parameterizations that represent better the UAE environment and the atmospheric processes and their interactions. Discrepancies in the model may result in misrepresenting the climate projection, for example, and also limit the use of our model for the forecast of convection, which could be used to guide cloud seeding operations. So there is really a need to continue the effort in assessing and improving the parameterization to better represent the UAE environment and the components, starting from land to sea to atmosphere and atmospheric compositions as well. Because this need is even made more urgent with the climate projection, which project that desert regions are expected to, in the future, to experience the most highest changes related to global warming. So if I can conclude with some recommendation that can be points of discussions in this forum, I'm welcome to take any comments or feedback from all the audience. So here we need actually to have more resources, for sure, more resources are needed to improve the different schemes in the model. But also we need long-term observations long-term observations that can help us to validate the model. And we do need to implement new techniques such as AI and to assess the model and validate against observations. So continuous support is actually needed. And here I would like to thank you all, and I'm happy to take questions at the panel. Thank you.
Thank you, Dr. Francis. I now welcome Dr. Ricardo Fonseca to give his presentation on convection over the United Arab Emirates and implications for cloud seeding operations, observations, and modeling.
Thank you, Latifa. I'm going to present work done by our team at Khalifa University in collaboration with the NCM. So, despite the hyper-arid conditions, we do see precipitation in the UAE, most of which falls in the cold season from December to March in association with mid-latitude weather systems. However, as previous speakers have pointed out, summertime precipitation isn't unheard of. In fact, we can see substantial accumulations of rainfall at isolated locations in the summer, and most of this convection takes place in the eastern side of the country. Here you can see in the middle and in the right panels two snapshots of radar reflectivity at 13 UTC, 5 p.m. local time, on the 4th of October on the left, and on the 10th of August on the right. And they both highlight the preferred regions for summertime convection. So these convective cells, they develop around the Al Hajar Mountains, and then they gradually push westwards into the UAE. Convection also occurs in central and western parts of the country. As other speakers have noted, numerical models, including the WRF model, have shown reasonable skill in the simulation of convective events in the UAE, meaning that their forecasts can be used for guidance into cloud seeding activities that are regularly conducted in the country, in particular in the warm season. Now, let's take a step back and look at the occurrence of organized convection in the country. So here you can see the number of days in the 20-year period, March 2020, at the location of the 5 major airports in the country, where we have detected the passage of a mesoscale convective system. What we did was to take a satellite-derived infrared brightness temperature that's available at a 4 km spatial resolution and 30-minute temporal resolution. And then we have counted the number of days at the location of each of these sites when the infrared brightness temperature was lower than 240 K, which we used as the threshold to identify MCSs. After that, we look at the individual snapshots, and we selected those that corresponded to larger scale convection. So we found that the majority of the organized convective events in the country take place in the spring months of March and April, although for Alain, shown in red, we see a secondary peak in the summer months associated with convection that develops along the Al Hajar Mountains. So we decided to look further into this to try to understand what are the processes that favor the development of MCSs in the spring months. And what we did was we took IREF 5 data, we extracted the anomalies, averaged over all the MCS days in March and April over the UAE. And here you are looking at the anomalies of some of those fields. The plot on the top left shows in shading the 2-meter temperature. The arrows give the 10-meter winds. The one below shows in shading the 2-meter water vapor mixing ratio. The arrows give the 850 hectopascal winds. The plot on the top right shows the 200 hectopascal wind. The shading gives the magnitude. The arrows give the direction. And the one on the bottom right shows in shading the 500 hectopascal geopotential height, and the arrows the 200 hectopascal winds. Again, these are anomalies with respect to the IREF 5 40-year climatology, averaged over all the MCS days in March and April that we counted. You can see that during the days when we have MCSs over the UAE, we typically have an anomalous low pressure over southern parts of the Arabian Peninsula, and the associated circulation brings in the warmer and more moist air from the Arabian Sea into the region. At upper levels, we see a southward displacement of the subtropical jet, and we also have a mid-level trough that leads to an unstable stratification. Now, during the summer months, we have a different large-scale picture. In particular, the 2 major processes that at larger scales that help in the triggering of convection in the region are the Arabian heat low and the intertropical discontinuity. We have decided to look further into these features, investigating their mean state and variability using IREF 5 reanalysis data. Now, the Arabian heat low is a thermal low. It's more pronounced in the summer season when we have a stronger heating of the surface by the sun. And thermal loads are typically identified based on atmospheric thickness or sea level pressure criteria. We have considered several, and in the end, we have decided to define the AHL based on the low level atmospheric thickness following Laweis's criterion that has been widely used for the Saharan heat low, so its counterpart in the Saharan desert. As Dr. Diana pointed out, the ITD is the boundary between the hot and dry air from the desert and the cooler and more moist air from the Arabian Sea. It's a convergence line, so it aids in the development of convection in the region. Typically, the ITD is diagnosed using wind or moisture metrics. We have considered some. In the end, we have defined the ITD as the line for which the 2-meter dew point temperature is equal to 15 degrees. So now I'm going to show you how these features look like. First, the Arabian heat low, shown here for the months of June to September. So the heat low is more pronounced in July, where we normally have the highest surface near surface temperatures. And it has two main cores, one along the Arabian Gulf and another one in central parts of Saudi Arabia, even though they are linked to each other. These are the regions where we have the highest near surface temperatures. And for the Arabian core, we also found that there's a dynamical forcing coming in here. So we have low-level convergence of downslope winds from the mountains, the Shamal winds, and the monsoon winds from the Arabian Sea. Now, regarding the ITD, here you are looking at its annual variability. The ITD is given in blue. The red arrows give the 10-meter wind vectors. You can see that the ITD is mostly along the Arabian coastline, but in the summer months, it shifts northwards. And in particular, from July to September, it can move over the UAE and help in the triggering of convection in the country. Now, this northward shift is more pronounced in the evening, nighttime hours. You can see that clearly if you look at the diurnal cycle of the ITD. It's summarized here. So the red color gives the ITD position at 00 UTC, the green at 06, the blue at 12, and the orange at 18 UTC. In the cold season, there's hardly any diurnal variability, but if you look at the months of July to September, you can see a jump in the ITD by up to 10 degrees in the evening, nighttime hours. And this is because we have an intensification of the heat low during daytime. The sea breeze comes in from the Arabian Gulf, from the Arabian Sea, and as the more moist marine air makes its way inland, this allows the 15 degrees Celsius isodrosotherm to shift northwards into the Gulf and southern Iran. Now, in addition to this more climatological work, we have also done modeling work. Dr. Diana summarized the large-scale conditions during the 5th of September 2017 convective event. So we had a trough over this region extending from Iran and Pakistan, and at lower levels we had convergence of the flow from the Arabian Sea, from the Arabian Gulf, and the Sea of Oman. Now, on this particular day, we had our microwave radiometer on the mountains, so around here. And on the right, you can see on the 5th and on the 6th of September in black, the 5-minute measurements of air temperature, surface pressure, and wind speed. If you look at the data you can see the passage of two MCSs, one on the 5th and a second one on the 6th. They are characterized by a sudden drop in air temperature, an increase in wind speed, and by their characteristic signature in the surface pressure. We ran WRF down to a spatial resolution of roughly 830 meters, and the WRF predictions are given in red. You can see that the model misses the event on the 5th, but it has somewhat of a signal on the 6th, even though it's a few hours later than in observations and the timing isn't quite right. We then performed semi-idealized runs, and one of them is shown in blue, where we artificially double the amount of soil moisture at all grid points in this nest. And when we do so, we found that the MCS signatures in the model predictions, they become of a larger magnitude. And even the timing with respect to the observed features is improved. This highlights the importance of properly capturing the soil moisture to simulate at least this particular summertime convective event, which is something that Dr. Diana alluded to in her talk. That's all from my side. I leave you with this slide where I list the most recent papers published by our team. Feel free to look into them, and then if you have any questions, you can just ask me during the panel discussion. Thank you so much.
Thank you, Dr. Fonseca. I now welcome Dr. Stephen Griffiths, Senior Vice President for Research and Development at Khalifa University, to moderate the audience Q&A panel discussion with this session's 4 presenters.
Good day, everyone, and welcome to the panel portion of session 4 of the 5th International Rain Enhancement Forum. We've just seen 4 great presentations, and as you can tell, we're going to tap into a broad range of expertise in the panel section to think about ways to advance the field of rainfall enhancement, particularly focusing on innovations and new insights that we can gain from our panelists. So we're a little bit behind schedule, and we'll keep the questions short because of this. I would like to start off just by following on Ricardo. Ricardo, your work and what you discussed was quite interesting with regard to modeling. You talked about how convection happens over the UAE. Can you explain ways in which your insights from the modeling can be used to actually help with the forecasting and prediction of seedable clouds? You didn't really get into that too much. I thought we might start off with a discussion with you about this. We'll get Ricardo when he's back on stage. We'll start with Diana. We'll start with you for a discussion of the modeling work. So Diana, again, very interesting work you've done with modeling. You started off by going through what you've done so far with the work and finished off by talking about where the modeling work may be headed with regard to impacts from climate change. Can you say a little bit about how climate change may influence your work in the future? I think this is a question that's interesting for many people that are following the weather research modeling domain.
So based on the latest reports from the ICCP, we can see, for example, that for arid regions, the climate change will be very pronounced in the future. Although some studies are pointing out to the occurrence of more rain over these areas, but on the other hand, the temperature will be extremes as well. So, and since convection and the occurrence of convection and rain involve both of these parameters, I think we need actually to assess how our models are able to represent this under different scenarios. But in order to achieve that, we need first to be able to simulate the current time. What are the situation, the conditions during our present days, and enhance the capabilities of our models to at least represent accurately and reasonably the conditions that we are witnessing in, let's say, in the last 2 decades, let's say. So we can later use them to do projections.
We'll go to Linda, though. I think the technology work that's been done and discussed in the panel is quite important for innovation. Linda did a really nice job in the presentation of talking about her cold cloud seeding materials. Thought that was quite novel. Linda, I know you've also worked on warm cloud seeding. Can you say a little bit about where the state of that work is and what you've been doing to progress that for utilization by an organization that's now doing cloud seeding?
Okay, yeah. For this project, can you hear me? Okay, here?
Yes, very well.
Can you hear me? Yes. Yeah, it's a delay. I found there is some delay. That's probably. Yeah, the project I worked in the first cycle, including both warm cloud seeding materials and the cold cloud seeding materials. So far, the project has been finished and the warm cloud seeding materials has been nicely scaled up into production, still in a pilot case, like few hundred kilograms, and NCM with the other partners in overseas in US to testing the field experiments, field operations. Due to the delay of the pandemic, so there is a slowdown, but eventually we will have opportunities to see the results. And for the cold cloud seeding, as I said today, well, it's still in the scientific stage.
Do you have any estimation how long the cold cloud seeding material development may take to get to, say, the stage where you're thinking about scaling it up?
Yeah, yes, there is a major difference of the cold cloud and the warm cloud. Say the warm cloud material has a very specific use, which is for warm cloud seeding. But this cold cloud seeding material seems has a more broad application, like hail suppression, you know, and also snow making. So I see this is a more interesting material as well. But it will span from only cloud seeding to something more.
Thank you, Linda. Martin, interesting presentation. And as I said, we'll focus a little bit more on the technological things that you've been doing. In your work, looking at the electrostatics and clouds, I found that interesting. It's something that we don't think about every day. You talked a lot about how there's a lot of work that's been done and you make good progress, but you didn't really draw a conclusion or what you think is the conclusion about the potential for electrical interactions in clouds to stimulate rainfall. So where do you think your work will ultimately go toward being useful and relevant to the organizations that are looking at cloud seeding for practical application? Can you say something about that?
So yes, thanks for the question. So I think there might be 2 sort of directions that you could identify. The first one is the direct injection of charge into drop populations at the stage, so that's at the lower cloud boundary, typically where the collision and coalescence process is only just starting to become active. And the charge is projected to help increase the conversion rate from drops to from cloud drops to rain by several percent over the lifetime of the drop population. So it will be as a direct seeding agent. It could be quite easily applied, and some of we haven't planned any test flights on that yet. But it's because it's the apparatus is quite compact. It can be easily incorporated in current seeding aircraft operational aircraft. And the second line, as I alluded to a little bit in the talk, was this idea that as soon as, certainly in warm cloud seeding, that the hygroscopicity of seeding material goes back when the aerosol gets hydrated more and more. We envision that charging up of such drops and aerosol will actually maintain the hygroscopicity, because one of the complex electrostatic interaction between drops and aerosols is that it's dominated by, at close range by image charge interactions, which are always attractive. And so that will produce the required hygroscopic effect at any size or at any salt concentration or whatever. So that is something that I'm seeing might be the future, where electrification of seeding material will aid the hygroscopicity of the material further down in the process. So not just at the initial stage of the process of attracting water vapor to the seeding material, but also later on when the drops are being formed.
You also talked a lot about the role of dust, because dust, of course, accumulates charges, and that's having an impact on the types of things you'd be seeing. Do you believe that your work is going to be very regionally specific, where there's some places of the world, the Middle East, for instance, that have very high dust concentrations, having different levels of impact on the effect of the electrical interactions that you can possibly stimulate?
Well, I think that must be true, yes. And this is exactly the reason why we're, of course, doing this project, trying to sort of get a handle on the different electrical environments in the UAE and other parts of the world that we have done measurements already. I mean, it's clear that the UAE, the environment of dust, is very highly electrified, and it does change the perspective a little bit on seeding with charged material. So, for example, one of the outcomes of the modeling work is that there is a potential for, if there's a high concentration of charged dust, it would make the drop spectrum too small, and the charging would actually help to keep the drop spectrum small. So in that sense, it would lead to a suppression of larger drop formation and rain formation. But having said that, I've also mentioned that the UAVs can inject charge of either polarity in the environment, and it's perfectly possible if the environment is highly charged of one polarity, we can extract that charge and thus mitigate for the suppressing effect of charge in those kind of environments. So it's very environment specific, and we expect, and because the UAE is such a it has all the highly charged aerosol and dust in the environment, it's a much more complex situation, and it's very clear that more work is needed to sort of disentangle the two, the kind of the suppression effect due to charge, but also the enhancement effect due to charge, which happens in different circumstances.
And taking that thought over to that,
much more complex environment.
And well, taking that thought over to Diana, you talked quite a bit about dust in your presentation. I thought that was fascinating. Can such work as Martin's, with the electrical interactions, the impacts of dust, be brought into the types of modeling work you're doing, or is that something that would take some time to build into the types of frameworks you've been working with?
It would be actually very interesting to combine both, yes. I believe based on the previous studies, especially on the dust over Africa, for example, where the electrification of aerosols in the atmosphere helped to dust and also impacted other processes. So this would be very interesting to look at in the near future.
That's good. We'll look forward to that. Sounds like an exciting path forward for the modeling work. I'd like to go through, and from the perspectives of both technology and modeling, hear from each of the panelists. Now, unfortunately, we only have Diana to talk about modeling. Where you see the highest impact work happening in the next 5 years? In your domain, whether it's technology or modeling, what would you like to see happen in the area of rainfall enhancement, starting with Diana in the modeling world?
I would say the modeling is still a bit lacking behind technology. Many understandings have been discovered in recent years, but still are not represented in the models. So I would hope to see a lot of progress on the modeling side in the rain enhancement area.
Thank you. Linda, we'll come to you for technology. Great work on the cloud seeding material. Would you think we need more materials work, or would you go in a different direction with innovation and technology?
Yeah, at least the outcome of the field operations evaluation of the warm cloud seeding material will provide fresh information and confirmation of the performance of this new material. I think that is a very important milestone. Looking forward to that. And for the cloud seeding material, I want to, people maybe not necessarily in the rain enhancement or weather modification, but it could be in the agricultural or the even result type of people might be interested.
No, we'll look forward to that. I know there's been not so much innovation as you showed for many years in the cloud seeding material domain. So what you're doing is quite a contribution. So we thank you for that. Finally, Martin, what would you like to see? Does it have to do something with electrical interactions? Would you go some other direction with innovation?
Well, I think, as you can imagine, I would suggest to consider electrification of both drops and aerosol as a way forward. Well, so just two things. I mean, there's a technology and a science goal, of course. The science goal is continuing. We're starting a PhD project with someone working at NCM to continue on the electrical characterization of the environment. So that's something we're quite excited about. And in particular, we're interested in something that we weren't as much aware of before we started our work in the UE, namely that there's quite a lot of fog events happening there. So we're trying to sort of do some work on that aspect as well. But I would argue, Stephen, that the ideas we have around electrification of aerosol, these are actually incredibly easy to implement in an operational sense. And so it seems probably much more easy to implement than the sort of complex materials that Linda is trying to sort of inject in the cloud. And that she has success with at the moment. So what I suggest is that this is something that we would be amiss if we wouldn't try this out. The prospects are very good, and I think the technology is fairly straightforward.
Well, we appreciate that, and I'm always happy to see people supporting their own work and promoting it, and I agree with you, there could be great things that happen. Unfortunately, this is all we have time for today, so I'd like to once again thank our panelists, excellent presentations, great contributions during the panel session, we thank you for that. And to all the guests, we'll look forward to seeing you in the next session. Thank you.
Thank you.
Thank you very much to our moderator and panelists for this opportunity to learn more about how to innovate in meteorology and rain enhancement. We will now begin the third session of the day and final session of the IREF on evaluation of impacts of rain enhancement efforts. Professor Petteri Talas, Secretary General of the World Meteorological Organization, will give the session's opening remarks.
Greetings from Geneva, from World Meteorological Organization. Here in Switzerland, we are suffering because of the COVID, and I have understood that that's the same in United Arab Emirates. And I would like to congratulate you for a very successful vaccination program. You are one of the leaders worldwide in vaccinating your population. Will get rid of this problem by next year. Now we are talking about the rain enhancement program that you have been carrying out for the past years, and we are very grateful for the financing of that program, and it's a very important program for many countries worldwide. We have more than 10% of the world population which are suffering because of lack of water, and because of climate change with higher temperatures, this problem is becoming more and more severe, and we have to tackle this problem. And the means to enhance rain and stimulate more rainfall, that's very important question, and it's also a very important scientific question. And we are of course all hoping that there would be positive outcomes of this program. Because of climate change, we expect that this negative trend will continue until 2060s, and that means that we will see regions worldwide where we will have both higher temperatures, more evaporation, and also less rainfall. On the other hand, we will see also areas which are going to have more rainfall, and we will have more flooding problems. But My personal main concern related to climate change is what's going to happen to rainfall and how much we are going to see more drought worldwide, because that's an obstacle for human life, and especially the less developed countries, they are suffering because of that. That's the case in many African countries where the basis of economy, basis of employment, and also survival of human beings is related to agriculture. And if we are able to enhance the amount of rainfall, that's highly important. Besides that, we have to pay attention to climate adaptation and improve the early warning services and also the seasonal forecasts. And as WMO, we are working for that goal. But all in all, we are very grateful for the United Arab Emirates for this program, and we have learned much more by doing good scientific studies based on your financing. I would like to wish you all the best for this meeting and all the best for the future of this program. Thank you.
Thank you, Professor Tallis, for this insightful speech. I now invite Professor Haneli Korhonen, UAE Rep Second Cycle Awardee, to give her presentation on the role of aerosols in efficient cloud seeding, key findings from the OASIS project.
Good afternoon, everybody, and thank you for the opportunity to present our work. Before we get started, I need to acknowledge my team. This has been a great collaboration between 3 institutes and about 20 people in the team, so from the FMI, Finnish Meteorological Institute, as well as from the universities of Helsinki and Tampere. So I'm going to present some results and conclusions from our second cycle project. And OASIS stands for Optimization of Aerosol Seeding in Rain Enhancement Strategies. Our project consists of 3 parts. We did a 1-year field campaign close to Al Daid in Sharjah, where we did a comprehensive characterization of ground level aerosols and also vertical profiles of aerosols, clouds, humidity and winds. And we obtained quite a unique data set for this region. In the second work package, we did 3 types of modeling. Firstly, regional numerical weather prediction modeling to characterize conditions at which clouds and precipitation form in the region. Secondly, cloud scale modeling, where we looked at optimal seeding strategies with respect to aerosol characteristics and ambient conditions, using both the numerical weather prediction simulations as well as the observation campaign data. And lastly, we did molecular scale simulations where we looked at optimal surface characteristics of ice nuclei. I will not talk about this strand today, though. In the third work package, we used artificial intelligence methodology to identify whether clouds susceptible to seeding are forming at a given atmospheric condition. And this is a topic that my colleague, Dr. Juha Tonttila, talked about yesterday, but I will touch upon it briefly also today. So let's first focus on the measurements. The main message in terms of efficient operational cloud seeding from our measurements is know your vertical profiles. And our observations strongly suggest that a key to successful rain enhancement is reliable information on the aerosol profile, the cloud profile, wind profile, and humidity profile. And we'll start with aerosols. So it's crucial to the problem, obviously, these aerosols, as have been discussed in this forum already several times, because all cloud droplets and many of the cloud ice crystals form upon aerosols. And of course, seeding then adds further CCN-sized aerosol to the cloud layer. And our measurements reveal that in the UAE atmosphere, the aerosol is actually, or the aerosol layers are highly varying, and they're quite complex. And this is relevant because the concentration and also the type of aerosol at the cloud altitude impacts the cloud characteristics. Now, the right-hand side show measurements of aerosol vertical layers during 2 different days. The time is running on the x-axis, the altitude on the y-axis, and the color indicates the strength of the signal or how much aerosol at a specific time there is at a specific altitude. And it's easy to see that on these two different days, the aerosol layers are very, very different, with possible impacts on cloud properties, of course, depending on the altitude. On the bottom left figure, on the other hand, there's a summary of the number of aerosol layers and their altitudes throughout the measurement period. And we can see that there are frequently at least 3 or 4 distinct layers in the atmosphere, as indicated by the yellow and red colors. Not shown here, but we've also done air mass trajectory analysis on the source areas and hence on the aerosol types in the UAE atmosphere. And we can see that the source areas differ quite a bit at different times. This because it impacts the aerosol type, then it also impacts the cloud properties. For example, the dust characteristics are not necessarily the same if the source is very local compared to the dust being transported from Sahara. So we believe that some information on the source region is also relevant for operational activities. And overall, we find that about 2/3 of the air masses arrive either from the Saharan region, the Mediterranean region, or north across the Gulf of Arabia. But let's move on to clouds. Here in this figure, I'm showing the monthly statistics of cloud top, cloud base heights, and also the thickness of the clouds. And the main message here is that the clouds reside at quite high altitudes. So if you look at the middle figure, which shows the cloud base, you can see that the typical cloud base, or if you look at the 25th percentile or the low end of the box symbol, the typical cloud base is above 4 kilometers in March and even 9 to 10 kilometers in December. And the implication for the efficiency of cloud seeding is that the precipitation that is forming in these clouds has to fall through a substantial layer of atmosphere before reaching the ground. And this is highly important because our measurements of vertical profiles show very frequent elevated dry layers with relative humidities below 5% in the atmosphere. And this is indicated in gray in the upper plot for one day. Or actually, this can only be measured at nighttime. And these layers are also quite thick, as shown in the lower plot. So the layers vary easily from about 0.5 kilometer to 2 kilometers and even thicker than that. So when the cloud layers for potential rain formation are above the dry layer, there is a challenge for cloud seeding in that there's quite strong evaporation of rain as it falls through this deep dry layer, as was pointed out earlier. Now, based on this profile data that we measured, we conclude that informed cloud seeding requires information on the vertical profiles during the seeding window. And there's no one single source that can provide all the needed information. Instead, we conclude that the combination of ground-based remote sensing, satellites, and numerical weather prediction tools would be required. LiDARs and radars on the ground can provide information on wind and cloud profiles, and depending on the LiDAR type, for example, possibly also on humidity or rough estimates of the aerosol. If satellite data is available for this period in question, it can provide information on aerosol sources and hence also potentially on aerosol type. And numerical weather prediction is needed for a broader context, like a 3D picture of the situation. And this is, of course, crucially important to assess the seeding opportunities. So we also conclude that ideally, an in-sample prediction system to produce probabilistic forecast of seeding potential would be very beneficial. Our cloud scale modeling work also provides further information on seeding efficacy. Dr. Juha talked about this topic in detail yesterday, so I will just reiterate the main conclusions. Our modeling indicates that even with hygroscopic flare seeding, most rain enhancement comes from mixed phase processes. And on the left, you can see the precipitation mainly from a simulation in which the precipitation comes mainly from the warm phase in the cloud. And on the right, you can see a case where it mainly comes from the cold phase. And it is easy to see by comparing these two figures that the surface precipitation enhancement as response to seeding is an order of magnitude larger in the cold cloud. Please note the y-axis scales, which are not the same in these two figures. We also see that the highest rain enhancement is in clouds that have weak to moderate precipitation and moderate riming. And these are the cases in which a collision coalescence and hence riming processes are relatively inefficient. And hence this injected seeding aerosol can accelerate these processes that are important for precipitation formation. But naturally also other processes such as humidity are important and play a big role. Dr. Juha also talked about our neural network-based proof of concept type of tool, which was developed to identify whether cloud conditions susceptible to seeding would form at a given atmospheric situation. And I will not go into the details here, but just say the sort of the conclusion that our first result indicate that there is potential in this type of an approach for further development if we aim to forecast the efficiency of seeding in different meteorological conditions in operational settings. So my conclusions based on our project when it comes to the effectiveness or the impacts of cloud seeding are that informed operational seeding requires adequate forecasting of vertical profiles. And this can be obtained from a combination of different types of measurement instrumentation and then with ensemble-based numerical forecasting. We also conclude that understanding and forecasting mixed phase processes are important in the UAE atmosphere, and we have taken the very first steps in the direction of providing a tool approach to do this forecasting, but obviously a lot of more development work would be needed in order for it to become operational. We've also identified several future research needs. Firstly, the optimal ways to combine observations and initiate ensemble numerical weather prediction for seeding purposes should be explored. Secondly, we need much more in situ airborne measurements in clouds to improve our understanding of the mixed phase processing. And luckily, I think the next presenter is going to present some new results on that. And finally, we've identified that we need further research into these AI-based tools so that they could be developed for forecasting purposes. Thank you very much.
Thank you, Professor Korhonen. I now welcome Dr. Paul Lawson, UAE REP Second Cycle Awardee, to give his presentation on Airborne Investigations of the Microphysics of UAE Cumulus Congestus Clouds and Potential for Rain Enhancement.
Hello, everybody. And I want to acknowledge first my co-author here, Dr. Roelof Berendtjes from NCAR, who was the flight scientist on all the missions that I'm going to report on today. And my reporting will be on the microphysics of cumulus congestus clouds, the clouds that Professor Hunneley suggested were the most conducive for enhancing rain in the UAE. Well, here's a photograph of a typical cumulus congestus cloud taken during our 2019 summer program. And on the right side is a picture of the Learjet that we used for the investigations. So I'm going to incorporate results from other locations as a background here to show how the clouds in the UAE fit into the spectrum of clouds that range from the tropics to the high plains in the US. And we've investigated clouds in all those areas. The Learjet, as most of you would know, is equipped with an extensive suite of microphysical instruments, many cloud probes, some with redundancy, PCAS for aerosol measurements, and air motions. using a names 20. Now in this next slide, we go through the hypothesis, but I'm going to skip this and just talk you through it, showing an illustration on the following slide. This is a pretty busy slide, but please focus on the left side here. And we're showing a cumulus cloud, a cumulus congestus cloud with a top at -5 centigrade and a very warm base. This is over the tropics near the Caribbean, or some of the measurements were made out over the South China Sea. And cloud base here is plus 23 degrees C. So we showed just the evolution of the coalescence process in these clouds before the ice phase starts. And you can see from cloud base to 0 degrees C to -5 C, there's a strong coalescence process with a big tail and millimeter drops forming. Now in the middle portion of this slide, we're showing that the cloud has grown and increased in height up to about -12 C, which is a typical stable layer height in the UAE. And at that point, there are rare ice nuclei that are active. They're very rare. They're about 10 to the -4th per liter, according to Dumont's work. But they do freeze an occasional large drop, millimeter drop. And when that happens, some of these drops will fracture, produce what we call spicules, and produce a lot of small ice particles. This stimulates a natural secondary ice process, which in effect will start producing small ice particles throughout the supercooled region of cloud. And if you look over on the far right here, what we're showing is the cloud where the supercooled large drops, the millimeter sized drops, are fractured, produce small drops. There's a differential fall velocity between the large drops and the small drops. So they collect, the small ice particles. So the small ice particles impact the large drops, freeze them, and we have this avalanche process, which we like to call a natural secondary ice process. So now if we had a cloud, if we go back to the left side, which had a cold cloud base, say +5 or somewhere in that area, 0, there's very little warm cloud to develop this coalescence process. And we found in the Idaho, Wyoming, and so forth, we don't see any large drops forming. There's no coalescence process at all. On the other extreme, the one I just explained, when it's a very warm cloud base, like +20 or +23, we get a natural coalescence and ice process forming. Now in the UAE, the cloud bases are around +10. So we're in the middle. So the question is, can we hydroscopically seed these clouds with an appropriate material and increase that coalescence process so that then, once the large millimeter-sized supercooled drops have formed, the rare nucleation event from primary nucleation, as nucleating particles, will freeze a few of them, but then the avalanche process will start and will enhance rain. As Professor Hanley said, the ice process is one whereby there's a lot more precipitation coming out of the clouds. And this is kind of an intuitive thing, because if you can increase the ice process, accelerate it, and produce rain before the cloud entrains dry air and dries out, then we get more precipitation out of cloud base. So I'm going to the next slide now. Okay. All right, this one is busy too, and I'll try to guide you through it. These are droplet-sized distributions in the all-liquid portion of clouds. They're at different temperatures depending on where the cloud was investigated. Now, if you look up in the upper right at the table, you'll see the red lettered clouds, I guess I'll call them, from the Caribbean, South China Sea, Philippine Sea, even in the southeast US near the Gulf of Mexico, all warm cloud bases. And then if you look down at the size distributions that are in red colors, you'll see they extend out to very large millimeter sizes in high concentrations. On the other end, if we go down below on the lower left part of the chart, you'll see the bluish colors in the high plains of the US, and you see that they don't develop large drops at all. Now, intermediate are clouds that we've investigated in West Texas, in Southwest Nebraska, and the UAE. Those are kind of the sandy and yellow colored ones. They do produce a few large drops, up to, sometimes up close to 1 millimeter, but they're very sparse. So there's not enough there to really produce this secondary ice process in an effective way. And that's what we're really trying to do in the UAE, is to find a way to stimulate the coalescence process and then let nature take its course. Now I'm showing, I'm going to go back. Okay. Sorry, little delay there. I'm showing cloud drop distributions at cloud base. And this is important. This is right above cloud base, a few hundred meters above. And if you look at the red droplet distribution, that's over the high plains of Colorado, and you see the drops are very small. Maximum size is, in this case, 20 microns. If we look at the black trace from the Caribbean, you see that they extend out to something like 80 microns, at just above cloud base. Now, interestingly, the sandy colored trace is an average from the UAE, and there's even larger drops at cloud base in the UAE. But what's missing in all of these droplet distributions, except for the Caribbean, is a high concentration of drops between about 15 and 30 microns. That's the gray shaded area you're looking at. Now, why are those important? They're important because the very smallest drops, the 5 to 15 micron drops, do not collide very often with the very larger drops, the 60 to 80 micron and larger drops. They go around the drop as it falls, and they go around its wake, like you've seen a bubble go around the wake of a boat. The drops that are from, say, 30 to 50 microns are falling at about the same velocity as the larger collector drops, the ones in the 60 to 80 to 100 micron region. So they don't collide very, very often either, because they're falling at the same speed. So we need these drops in the 15 to 30 micron region. And this is substantiated by laboratory work too, showing the collection efficiencies of different size drops. Pinsky et al. Has a very good presentation of this. So now I'm going to slip back to another view on the left here. This is a less complicated view of droplet size distributions, excuse me, at -5 in all liquid cloud, just showing a few of them. The black, again, being the Caribbean, and the red is the high plains, and those are the two extremes. And then you see I've shown West Texas and Amarillo, Texas size distribution in the UAE. And on the right side of that, because it's kind of easier to visualize, I'm showing 2DS images of these various locations. So where you see all the large black discs is in the Caribbean. And that's just indicating a lot of large drops. And then over in Amarillo, Texas, we have considerably less, but a few. And then the UAE, even less. And in the high plains area in Colorado, you don't see large drops. You might see 100 or 200 micron drop. So this, again, is sort of a visual representation of what we see as we go up in the cloud. So where do we go from here? We need to test various hydroscopic seeding materials, and we like to focus on the new nanotechnology material, which appears to have the most promise, although we have to do a lot of tests with it. So what do we propose? Well, one way to start would be to test the various hydroscopic materials in a continuous flow cloud chambers, such as developed at Michigan Tech. This is pretty experimental, kind of new, but it's the only way you can get a continuous development of the cloud droplets. Next, we still have to develop a reliable airborne dispensing technology. Right now, we just kind of like popped the material out of a flare shell, and it would be nice to be able to distribute it in a known concentration and over a nice spatial distance. And then if we find a candidate seeding material that looks promising, then as Professor Hanley said, we need to conduct more airborne tests. And this time we need to do it with a seeding aircraft and an instrumented aircraft and investigate the microphysical response to determine if the coalescence process appears to be sufficiently enhanced using the seeding material of our choice to support this natural secondary ice process. Then, if it looks like we are getting the result that we want, then we can move on to the next step, which would be a randomized cloud seeding project in the UAE, where we use, and we have to use, unfortunately, radar for the evaluation of the rainfall at cloud base. It's just impractical to set up enough precipitation gauges all over to do this. One final thing is that we'd like to be able to work over in the foothills of the mountains and even over into the Oman airspace. And I thank you very much.
Thank you, Dr. Lawson. I invite Dr. Sarah Tessendorf from the National Center for Atmospheric Research to give her presentation on Advances in Evaluating Cloud Seeding Impacts by Coupling Observations and Models.
Thank you so much for having me. Here we go. So today I want to talk a little bit about our work to do evaluations of cloud seeding programs. And first, I just want to lay out the landscape for the various ways that a lot of programs perform these types of evaluations. Over the many years that cloud seeding programs have been evaluated, observations are usually a key component of that. Many programs aim to try to get direct measurements of the seeding impacts. This is often very challenging to obtain because once you seed the cloud, you don't know what would have occurred naturally. And so to counter that, a lot of programs have attempted statistical program type of analyses where they run a randomized statistical experiment. This provides a more controlled experiment where you can have a control sample that's not been seeded and compare that with your seeded sample. But one of the challenges with a statistical program is that the weather is so variable that it's often challenging to have a statistically significant result without a really large sample. And a really large sample size can take years to collect in nature. So it's often been intriguing to run numerical modeling simulations to try to understand the effects of seeding. Cloud resolving models or parcel models have often been used for this reason. It's great because it does provide a controlled experiment in that you can run a simulation with seeding and without seeding effects and look at the differences. But as we all know, many models don't resolve all the relevant processes and they have uncertainties. And so those model simulations on their own still do not provide us all the answers that we need. Luckily, in the last decade or so, supercomputing has advanced so much that we can now run much more computationally expensive simulations. We can use approaches like ensemble modeling experiments that help create an understanding of what the model uncertainty is by producing a spread of results. We can run very high resolution simulations like the LES simulations we just heard about, or really detailed simulations like direct numerical simulations or DNS model, which simulate the individual particle by particles in a parcel. So all of these very sophisticated options are available. But really, even still, with all those nice sophisticated models, we still need observations in order to provide some truth, to provide some constraint on these models and help us understand what value they provide. So the approach that we've been taking at NCAR is to combine models and observations together. And we've been finding that this really has been leading to substantial improvements in our understanding of the impacts of cloud seeding. So I'm going to provide a few examples of this work where we've coupled some of these different approaches of model observations. The first one I want to speak about is from the SNOWY project. SNOWY stands for the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. This was a project that took place a few years ago in the mountains of Idaho. Our hypothesis here was that in winter orographic clouds that are fairly stable, widespread, not producing a lot of natural precipitation, but contain supercooled liquid water, that if we seed them with an aircraft, this would produce an unambiguous seeding pattern that would allow our research aircraft to collect measurements of those direct impacts of seeding and the seeding lines. So in this example on the bottom left, you have a cartoon showing a westerly wind, a seeding aircraft that would be flying perpendicular to that wind flow. And as it flies, non-natural zigzag-like pattern. And then that would allow our research aircraft to fly along the wind back and forth in and out of those individual seeding lines. In the vertical cross-section cartoon in the lower right, you can see what that would then look like, seeing those individual seeding lines producing plumes of ice and then snow as they fall to the ground. And our observational strategy was to also observe these conditions with radars that were positioned atop of the mountains, scanning these clouds as well. There we go. So using these aircraft, both the seeding aircraft and the research aircraft, and these Doppler on wheels radars positioned atop the mountains upwind of the region, we were actually able to measure this unambiguous signal in 3 cases. And this was a major highlight of the SNOWY campaign. And on the animation on the right, I'm showing one of these cases where you can see in the radar domain, this case was a southwesterly wind case. So the aircraft seeding track is oriented perpendicular to that wind flow as the yellow aircraft track there. And at the beginning of this animation, there's not much radar, there's not much echo on the radar screen. So these clouds were not producing natural precipitation readily. It's starting over now, you can see there's not much there, but then as the seeding starts, you'll see that zigzag pattern showing up directly on the radar screen. So this was a huge success for the program to be able to observe that pattern. More than that, in a moment, if you look here, right about now, you'll see a line of dots on the radar screen. And this was even more impressive that in some of those seeding legs, we only seeded with ejectable flares, which are released below the aircraft every 30 seconds or so. The rest of the time we were seeding with burn-in-place flares on the back of the wing, as shown in the picture on the left. Those burn continuously and produce that more continuous zigzag pattern, whereas the ejectables produced that dotted line pattern. So this was really remarkable that we were able to see this very unambiguous signature of seeding. And what's even better than that is that we were able to collect in situ measurements in these seeded plumes with our research aircraft and collect the radar data as shown here. So this was a huge breakthrough for us to directly observe these effects of cloud seeding in these winter orographic clouds. So some of the things we've been able to do with this data, we've been able to track those seeding lines to the ground using the vertical pointing radar data from the aircraft. So on the left, you can see each leg showing a time succession of those seeding lines falling to the ground. And then we can also track them in time with the Doppler on wheels radar, which showed that zigzag pattern. Up in the upper right here, we've zoomed it in over one of our precipitation gauge sites, Silver Creek, and you can then look at the time trace of both the reflectivity as it passes over that gauge site shown in the bottom right, and the reflectivity here is in gray. So when it's increasing, that's showing you that that seeding line is passing over the gauge. And then we look at the measurements from the precipitation gauge in the blue line, and you can directly measure and quantify how much snow fell when that seeding line passed over. Beyond that, we also have been able to map out the spatial extent and magnitude of these seeding effects in the 3 cases that we very clearly observed these types of patterns. And this is a paper that we recently published last year in the Proceedings of the National Academy of Sciences. And what you can see is there's, not each case is going to produce the same amount of snow. In the case on the left, there was up to about 0.1 millimeters around most of the areas that were being detected as from seeding. And in some of the other cases, it was up to or over a millimeter in some locations. This was for the first time we were able to map this out spatially like this using those data. But what's even more important is that we can now use these data, all these detailed measurements, to improve and validate numerical model simulations. So for example, the WRF weather model, which was developed to simulate silver iodide cloud seeding, is a great modeling tool to do numerical modeling evaluation of cloud seeding. But without these types of observations to help us know how well it's performing, we really don't know how much trust we can put in it. So that's exactly where we've been going now with our current research, is we've been running model simulations with WRF WeatherMod. As you can see, the animation on the left is showing a simulation of the zigzag pattern release and dispersion of silver iodide. We can compare things along the flight track between the model and those observations then, things like the particle size distributions over time in the seeding lines, which the observations in this example are shown in the upper right, with each of the different lines being a subsequent pass through the seeding plume. And then in the center left, you can see the same thing from the model. We can also compare total ice concentration between the observations in the model and many other metrics. We can compare those maps of seeding effect on the ground that I just showed you. We can compare those from the model as well with those observations. So what we're currently working on is using all of these wonderful snowy observations where we got those direct measurements of seeding effects to evaluate the model physics and then better constrain our model simulations to improve our understanding of the seeding effects in winter orographic clouds. With my last few minutes, I want to switch gears a little bit and talk about some of the work that we're doing in this respect with hygroscopic seeding as well. So I'm going to show an example where we have coupled direct measurements, in situ measurements from a randomized seeding trial that took place in Queensland back in 2007 to 2009. It was based in the Brisbane area, just along the coast in Queensland here, as shown in the map on the left. And in this program, as I mentioned, there was a randomized statistical seeding program. And for every single one of those randomized cases, the aircraft, we had a research aircraft that would collect cloud-based aerosol measurements, as well as it would ascend into the cloud just above cloud base to collect measurements of the droplet size distribution, the initial droplet size distribution just above cloud base. So we had those measurements for every randomized case. And one of the things that we started to see when we began our analysis was that there were different background aerosol conditions occurring. Given that this location is right along the coast, you can see that sometimes it has influences from the ocean and sometimes it has influences from the land. So we ran back trajectories as shown in the bottom map, and we categorized these based on how much time they spent over land versus ocean. And so these were determined to be more continental influenced trajectories versus maritime influenced. And what you can see in the bottom right scatter plot, this is showing the cloud condensation nuclei concentration versus the PCASP aerosol measured concentration, that the maritime influenced cases had much lower aerosol concentration, and the continental influenced cases had much higher aerosol concentration. So taking what we learned about these two different aerosol regimes, we then stratified the in-cloud measurements of droplet spectra from the randomized seeding trial by those aerosol regimes. So in the randomized seeding trial, we had some cases that were seeded and some that were not. And then now we further stratified that based on if they were maritime influence cases or continental influence cases. So the top two plots here are showing drop size distributions in a statistical sense. These are mean distributions over all of the sample of seeded in dashed line, unseeded in solid line, with the maritime influence ones on the left and the continental influence ones on the right. And when we did this, we were able to show that in the continental influence regime, there was a statistically significant droplet broadening in that initial droplet spectra. The natural unseeded droplet spectra was much more narrow, but when we looked at the droplet spectra from those that had been seeded, you can see that the tail of larger drops was much more evident, whereas there was not a detectable difference in the maritime regime. And we attribute this to the difference in their background aerosol size distribution, which is shown in the bottom plot here. that in blue, which is the maritime influence, you have this coarse mode of sea salt particles, whereas in red, the continental influence did not have that coarse mode. But when we seeded them with the seeding material, which is shown in the black curve at the top of this plot, we added those coarse mode particles, which then helped broaden the initial size distribution. Now, keep in mind, this was all based on observations. It was done in a statistical manner using the randomized seeding trial, so we don't have confirmed measurements inside the areas that were treated with hygroscopic seeding flares. So in order to further enhance our understanding of these observations, this is where we coupled this with some modeling. And in this case, we ran a parcel model to at least confirm, and that parcel model did confirm that the behaviors that we saw in the statistical analysis were in fact what the model supported. And the fact was that the model showed that clouds in the maritime influenced regime already had a broad droplet size distribution without seeding, as shown in the bottom left red curve, and that the seeding didn't really significantly alter that initial drop size distribution. But clouds in the continental influence regime had a more narrow distribution without seeding, which then became broader due to the influence of the hygroscopic seeding. And this is an important first step in the hygroscopic conceptual model to broaden that distribution, similar to what Paul just mentioned, to get those drops in the right size that can then help collision and coalescence. So I just want to wrap up with the summary saying that we've been able to take advantage of recent field campaigns that have been providing valuable data for cloud seeding research, such as those from SNOWY that collected that unprecedented data set for detecting the seeding effect in the orographic clouds. We've been using data from hygroscopic seeding trials and detailed measurements to study the impacts of hygroscopic seeding as well. And thanks to supercomputing, we have a new way forward for more sophisticated modeling experiments, such as large ensembles or DNS type model simulations. And so really, I believe that the future of cloud seeding research is really going to be utilizing the new supercomputing, sophisticated modeling capabilities coupled with the detailed observations that we have today in order to continue to make improvements on understanding the effects of cloud seeding. So I would like to finish by acknowledging the sponsors for this research and my many collaborators that I've worked with over the years on this research. And with that, I thank you for your attention.
Thank you, Dr. Tessendorf. I now welcome Dr. Robert Robinson, Chief Scientist at Science Prime, to moderate the audience Q&A panel discussion with this session's 3 presenters.
So I'll begin by thanking all of our speakers. Those were 3 excellent talks that really highlighted, the diversity of methodologies that are being applied to studying rain enhancement, but also in revealing some of the underlying physics that goes with rain enhancement. I'm welcome questions from the audience, and I suppose there'll be a way I'll see those questions if they come in. But maybe in the meantime, let me just begin by trying to capture your thoughts on this whole issue of evaluating impacts. And of course, one way, the basic way to evaluate impact is to see whether it rains or not, right? But of course, just seeing whether it rains or not, that doesn't really tell us where in the complex process of rain formation, what's working and what's not working, what are we missing? So maybe I thought I might get your views on what are the key observables that you might look at to see whether cloud seeding is actually working. And maybe I'll start with Professor Hanali.
Okay, thank you very much. Well, based on our research, we obviously want to look at the mixed phase, and as pointed out by the previous presenters, there are lots of ice phase things that we could look at, the ice number concentrations, the size distributions. We'd also be interested in different ways that we could learn about, like what are the processes that lead to this kind of a ice formation. So I think that would be very valuable when we plan how to do the seeding. In our case, of course, any information on the rime fraction, which we have identified as an important variable, would be very valuable. But in general, I would say that any in situ information on the mixed phase cloud would be great for validating and evaluating, for example, our modeling results.
So you've sort of highlighted the in situ measurements in order to
well, I mean, I'm sort of maybe talking from the point of view of our project. So, I mean, what we would need to validate or evaluate the validity of our results, I think that the in situ measurements are very important. But I do agree with the previous speaker that it is very important to combine all these different kinds of data sources. So in situ is important. I think ground remote sensing tools are very important. Satellite information where you can use them is very important. And then combining this all with the numerical modeling tools.
Sure. And so maybe I'll let Dr. Lawson follow up on that, just in terms of what are the observables and what are they in situ or remote?
Thank you, Dr. Robinson. In situ is going to be important because we have to look at the physical chain of events of what's happening. But what everybody wants to know is how much rain are we getting on the ground? That is a tough thing to evaluate because I think, as I mentioned at the end of my talk, it's just impractical to put out a dense enough array of rain gauges to be able to measure this sort of thing. You can try to have a mobile rain gauge radar unit that'll help. But I think what we have to rely on in the UAE are radar measurements, dual pole radar. And there are those measurements in the UAE, so we can use them effectively, and the modeling work. So it's really a three-pronged approach. We have to do the models to see if they will validate the physical chain of events we measure in situ. We have to have radar data to see just what is coming out of the base of the cloud. Because even if we have what we think is a nice process in the cloud, if we don't have more rain at the base, then we're not going to know. And then, as everybody has pointed out, a randomized seeding test eventually will be provide the statistics that will be needed, along with model support and radar.
Good. So Dr. Tessendorf, just and you showed some great modeling results, and the whole idea of combining observations and modeling. I guess that's what we're all sort of converging on, that aspect. I'm not sure I see how that goes with the statistical analysis. How would you do that statistically, applying that methodology?
So we've done it a few different ways. In the example that I just showed from the Queensland results, we relied on the statistical analysis from the Queensland observations in order to compare with the model results that we had. We've also done that with winter orographic cloud seeding results that we had out of Wyoming. There was a long-term statistical program there that like most, didn't have statistically significant results. And so we ran an ensemble model simulation with WRF WeatherMod to build up a spread of potential results from the model. And the first step in that was to compare with the statistical results and see if the model experiment could replicate those statistical results. The statistical experiments and the data that are collected in them are highly valuable still, even if the statistics themselves don't give you that significance that you were expecting. A lot of times these programs will have the statistical significance. Normally we want to have it greater than the 95th percentile, but sometimes it'll be, say, 80th. Is that meaningful? Well, when we run the model simulations along with it, we can really dive in a little bit more to the processes that are happening in these clouds and try to better understand what's going on and get a little bit more meaning out of that statistical experiment that just due to natural variability of the weather might not have actually had a high enough statistical significance to meet our expectations.
Yeah, I feel like that we've really come a long way in this program in demonstrating that cloud seeding really does work, and now we're just trying to sort of get a better assessment on the conditions where it works better, and how to apply some of that knowledge to the actual cloud seeding operations. You know, going forward, I see that it would be really advantageous to have a field campaign where we could do a really strong demonstration project that the seeding is effective, and not just effective anywhere. The seeding is effective in the UAE, which presents a unique set of challenges. I wonder if I could get you to think about or say something about how you would assemble, what are the components for a campaign like that? And maybe, Paul, I'll let you begin.
Okay, maybe a little clarity, Bob. A campaign in the UAE, is, you know, for evaluating the seeding. Well, I think it needs the three components we talked about. Well, we need a seeding aircraft and an aircraft to do microphysical measurements. Secondly, you know, we need the radar data. As Sarah showed, when you have the radar data and the in situ measurements, and you can combine them, then you have a much better physical correlation. And then finally, you know, if we can get model results that will actually reproduce, and it's hard to do on an individual case basis, but if we can separate out unseeded and seeded clouds and see if there's a separation there statistically, then I think we have a program that's going to be very convincing.
Hanalei, do you have anything to add to that? I was also wondering about whether there's a place for satellite remote sensing from satellites too.
And also remote sensing, I think, from the ground. So I think that the LiDARs that we have operated in the UAE would be very highly valuable for this kind of work, so that you could, this kind of an evaluation projects, that you could get information on the humidity profiles, the aerosol profiles, cloud profiles, and wind profiles. The satellite data, I think that is valuable when it's available. So, I mean, that is sometimes the problem, isn't it? That it might not be overpassing at the time when you need to do your seeding, for example. But I do think that when it's available, it can provide additional information. Perhaps I'm biased because of our project. I do personally feel that in situ measurements and perhaps the crowd-based remote sensing measurements would be the most beneficial.
Let me just chime in, Bob, just for a second. And, you know, with these cumulus congestus clouds that we're targeting, the pixel size from satellites is so coarse that we don't get to see a whole lot. You know, the satellite's going to give us a much better picture of very large storms.
Mm-hmm. Right. And Sarah, the modeling results that I guess these are not assimilative models in the sense that you could take in situ data or remote sensing data and run these models sort of on the fly to assess what current conditions are. Have you thought about that?
Well, yeah, so the WRF model and WRF weather mod can most certainly be set up to run in a data assimilation type setting if you wanted to run it in real time. We do run WRF and WRF weather mod in real time for some of our projects, but have not yet move to the phase of having data assimilation, mostly because some of the key data that we would want to assimilate is not always readily available. Sounding data and so forth like that would be really highly valuable to improve the model, to nudge the model's vertical profile of the thermodynamic environment, which is so important for cloud formation and getting the model to formulate these clouds and the phase of the clouds properly. But so yeah, that's certainly something that can be done. And if the right program were designed to have, you know, a nice set of additional observations to do that, that would be a great way to run the model. But we do typically run the model in a retrospective manner where we can force the initialization of the model with any number of reanalyses, and that gives us the opportunity then to set up either an ensemble where we run with lots of different initializations, or it just gives us the opportunity to test the model and figure out which configuration compares best with the observations that we have available.
Great, great. We're almost out of time, but I did want to get maybe your one last comments from you, because what's been so interesting in all these projects is how they've changed along the way. And it's based on this new knowledge that you've gotten and had to make changes. So maybe you could say, just give an example of one thing you know now that you didn't anticipate when you started your project. So Annalie, maybe you could start off there.
Well, thank you. That's a very interesting question, considering that I'm a newbie to the field, so I didn't have any experience on weather modification before I got this project. So I've learned a lot. But I think that the main two things that we have changed compared to the original proposal was that there's been, because we had this international advisory board who sort of guided us towards looking at the sort of the moderately convective clouds in the UAE. We perhaps were thinking of looking at a little bit different types of clouds at the beginning. And then our work package 3 actually changed completely during the project. So we were first thinking of building these emulators based on this cloud scale model. But then our results sort of pointed to a new direction, which we thought that was scientifically more interesting, but also I think that more useful for the operations in the UAE. And then we started developing this artificial intelligence tool, proof of concept tool. And that's, I think, that led to very interesting results.
Great, thank you. Paul, how about you? Have you gotten any new insight?
Yeah, what we learned that wasn't obvious, although maybe it should have been, is just how important the depth of warm cloud is in developing coalescence, developing large drops up higher in the cloud. So, and this reflects simply the temperature at cloud base, because we're talking about the depth between cloud base and the 0 degree level, if we're going to call it warm cloud. And this just wasn't apparent. And as I pointed out, in the UAE, there are very large drops at cloud base, mainly from salt coming in off the seas and salt being kicked up off the deserts. But that is not enough. We have to have a little bit more either depth of cloud base or drops in an intermediate size range in order to produce this coalescence.
Great, thank you. And Sarah, so have you learned anything that's been put into the models that have helped improve the models?
Well, most certainly we are certainly trying to, develop new ways to improve the models with the studies that we've done. But I think the comment that I would say that we've learned, and again, kind of like Paul said, maybe we should have known all along, is just how variable naturally and how variable clouds are naturally. Even in the winter orographic clouds from the snowy campaign, which I showed, very clearly, we can detect these unambiguous signatures of ice forming in some of them. They're stable clouds. You think that they're much simpler. But when we look with cloud radar, we see such really fine scale features in these clouds. There's so much, fine scale turbulent features and things that are occurring in these clouds that it's no wonder that it's been so hard over the years to get statistical significance in these types of statistical analyses, and why it's still so hard to get the models to reflect all of those processes. So, you know, the improved observational capabilities to better observe and see these small fine scale features, and then improve sophisticated high resolution models that can simulate them, I think that's really, really key. And with respect to the hygroscopic seeding, one of the other things that I think we've learned and shown in our recent research is that it's really critical to understand that background aerosol condition, because that's one of those conditions that's variable in nature. And if you don't constrain for that in setting up your statistical analyses, it's just going to have that much more natural variability in the study. And this goes for the winter orographic cloud seeding as well. The background aerosol, which has an effect on the ice nucleation, the ice nucleating particle properties, that also has an effect. But especially for hygroscopic seeding, I think it's very important for getting those in situ measurements to understand what your background aerosol is in order to better constrain and even use that perhaps as a variable in setting up a hygroscopic statistical seeding trial going forward.
Great, thank you. And maybe that's some good thoughts to conclude the session on our panel members for their presentations and for answering the questions. And we'll end the session here. And thanks again for everyone.
Thank you.
Thank you.
Thank you very much to our moderator and panelists for giving us this view into how we can conduct evaluations of rain enhancement efforts. Thank you to all of our speakers and attendees for helping us conduct a successful 5th edition of the International Rain Enhancement Forum. Despite the situation incurred by the COVID-19 pandemic, we have still been able to gather and share knowledge on rain enhancement research worldwide and plan for the path forward in the efforts to fight water scarcity. The contributions of all our participants give us great hope for the future and reassure us of the path forward in tackling these issues. Thank you very much. And a gentle reminder that if you have missed any of IREF's sessions, you can watch them on www.iref.ae. I would also like to remind you that the 4th cycle of the UAE Research Program for Rain Enhancement Science was launched yesterday, and all details can be found on www.uaerep.ae. Thank you very much, and I wish for you all to remain healthy and safe.